right, good morning, everyone.
Good morning.
Welcome to the Spring 2026 Design Challenge. Welcome everyone here live and everyone on YouTube. I'm Tim Urban, Director of the Texas Space Grant Consortium, and we are delighted to have such great projects from brilliant teams that we get to see this morning and afternoon. We have 13 teams presenting this morning in 4 different sessions. We'll go session by session according to the time in the schedule. And each team is going to have 10 minutes to present, 4 minutes for questions, and we've got a couple mics. We'll be able to run around to get your questions. There's the fixed mic here and one remote mic if you need it. And logistically, if you just stay on the side of the stage beyond these blue arrows, you will always be in frame of the camera. All right, so let's get started. Our first team is from Texas A&M, and they are the Agginauts.
Howdy! We are the Agginauts. My name is Emily Nelson.
I'm Sam Corden.
I'm Samantha Goebel.
I'm David Gonzalez.
And I'm Gavin Moore.
So our mission is to design and build an exercise device that maintains the cardiovascular health of astronauts while on extended missions. So one of the main things we're trying to mitigate is orthostatic intolerance, which is a group of conditions where a person experiences dizziness and lightheadedness, and I'll show kind of the cause of that. So pre-flight, you can see the astronaut in Earth's gravity normal, and then when they go up to no gravity, all the fluids tend to accumulate in their head, and then once they enter back into Earth's gravity, those rapidly are dispersed throughout their body, which leads to that dizziness and lightheadedness. So this happens in about 83% of astronauts that have gone on long-duration missions. So the need is to create a device to maintain the astronauts' aerobic capacity to help mitigate this. So one of the reasons we settled on the climbing device was because of the efficiency of this exercise form, and also because we can incorporate movements that also help to maintain other muscle mass. So previously, as you can see on the right-hand photo, we had a solid frame last semester, and we also had a preliminary resistance and harness concept and prototypes, but those were not yet implemented into our design. And we also were working on foothold design, but we weren't settled at our final prototype. So this semester, we've reduced the frame weight by about 40 pounds. As you can see in that lower right-hand photo, that's the pattern we cut in the frame. We added this acrylic cover on the front, new handholds and footholds. We added the harness system and the resistance system. We added electronic control to the resistance system, tracking of the movements through the VersaClimber app, and a fan.
We conducted a full-scale biomechanics study. So we used OpenCap to collect heel marker data for running and for climbing. So as you can see here, the running position data sees a lot more movement in the X, Y, and Z. Meanwhile, climbing, the heel marker data is constrained to the Z axis. So we use these to generate plots of range of motion for all major joints. And what we found is that there is a larger range of motion in the flexion extension of the hip and the knee. And this indicates more recruitment of your large muscles on your leg, like your quad and your glutes, which is good for the missions in this case. We also conducted a vibration analysis using the jerk of the motion, and we saw a 72.5 reduction in vibration in climbing versus running.
We also did fatigue analysis. The big takeaway from this slide is just if you compare running and climbing has that negative % change. So over a simulated 8 months, climbing would have less fatigue, be less affected by that.
So, like Samantha mentioned earlier, we did water technique on the actual frame itself. So you can see in that red image, we were able to cut out that material, and that was able to reduce the weight by 43.88%. And then we did a FEA with a vertical load of 1,300 newtons, which represents the 95th percentile American male, and we had a factor of safety of 47. And then here are some of our stress strain plots from that study showing minimal deformation.
And for the harness system, I'll just stay here. What we wanted to do is mimic vectorized bodyweight forces. All that means is imagine that this is like a triangle, and this is your height of the triangle towards the base, and then the harness system itself is like a hypotenuse, which is mimicking this sort of paper that we have here that talks about partial bodyweight loads and zero gravity. Lastly, we wanted the components to attach to a base, which here is wood, but in real life it might just be some bolts. And you have a static rope, which was able for us to like make different knots for different user heights, a carabiner to connect, and of course an elastic band kind of to mimic the bungee cords and to give us a little slack and generate tension.
So what we did next was we did a sweat degradation study to determine the material to use for the handles. So with this, we studied 4 different types of materials, and we determined that not only in under microscopic view, but also in percent mass change, the best option for this was the clear flexible resin that you can see on our handholds up there. Not only is it comfortable, but it's also the most resilient to this degradation. With this material, we then went through a number of iterations. So as you can see up here, we currently have the first iteration. We found that this might be a little too malleable. It molds to your hand a little more than what might necessarily be desirable. So then we went under 2 more iterations, including this sort of swirl pattern and this crisscross pattern. So another aspect that we changed is in the initial design, your hands were at a fixed length. That's not the most efficient way to be able to target each muscle area. So we had it designed multiple different lengths that you might be able to use. And to store these lengths when you're not using them, you can put them in these holes up here, just like so. Furthermore, each of these parts can just pop off and go onto the next bar, because even though the weight of these is minimal and negligible, every little bit of mass counts. And so this way we can just shift it onto the next piece even better. For the footholds, we looked at what they had on the cycle up in the ISS. And they have these clipless pedals used on the Peloton currently. So what we did to adapt this to make sure that it was good for your hips and joints and perfect for our device is we drilled a hole in the axle and we put in a titanium bar there. And then over that titanium bar, we put an aluminum adapter to ensure that it would screw in to our device and be perfectly load-bearing throughout the whole of it and support any weight that we would put on it. Furthermore, all of these can be adjusted to be up or down in height. There's 3 holes in each of the wheel systems, and so we can make sure that no matter the height of the astronaut, they can all fit perfectly onto our device.
So now starting with the resistance system, we're going to start with the end, which is the end caps. So our end caps are a multi-material part. So they have a PETG glass fiber for structural stability and a flexible TPU 95A to improve the sealing. This is then put inside a polycarbonate tubing. So it's clear to allow for fast inspection of the O-ring seals on the inside. We also machined a Teflon plunger to have minimal friction as it moves. From here, whenever the user moves the pistons up and down, it's going to be forcing air into a needle valve, as shown here. This adjustable orifice allows us to set the resistance, much like blowing through a straw of different sizes. Now, an issue with this is that at very small diameters, we see a very sharp increase in the resistance. This means that we need a consistent and precise placement of the needle valve. In order to do this, we use a stepper motor. Now, As you twist the needle valve, you see vertical displacement as it unscrews. So to account for this, we use a shaft coupler that is tightened to allow for unscrewing as well as vertical translation. It also has piston docking systems where it clamps in at the back and then unfolds like a DeLorean, and this is also multi-material with TPU to prevent slipping and PETG glass fiber for structural stability. We also perform testing on this, so using 150 pounds as our goal based on the 150-pound cable exercises seen on the ARED on the ISS right now, we met that goal with a safety factor of 1.97. For the electronic system, we have two systems. We have an emergency shutoff powering system 1, which powers the stepper motors as well as the cooling units. The MKS Gen 1.4 powers the stepper motors and is put inside a specially designed climate-controlled housing. This is because when exercising in a small space, there might be humidity building up, so this ensures that everything stays dry while staying cool. System 2 runs off a 12-volt, 5-amp power supply, and that's for the biometrics board. These have their own software systems, where the resistance system has an interface, as you can see here, allowing the user to type in the resistance level they would like, hit enter, and the stepper motors will automatically adjust. Meanwhile, the biometrics board at the back will be giving key features like the stroke length, as well as the rate, calories burned, watts, and heart rate, if desired. Lastly, for future work, we would like to reduce the device footprint by making it collapsible, integrating into structural beams to improve the vibration distribution, making it parallel to key structures. We also wanted to expand the biomechanics study to include zero-G testing as shown here, and a diverse patient anatomy. We also wanted to consolidate the resistance and biometric data streams into one app, expand material studies, use double acting cylinders to essentially double the resistance amount, and lastly, we wanted to improve the user engagement through VR environments and gamified exercise. And this is our outreach. We participated at Night at the ZAC with the Texas A&M Science Olympiad Society.
So here's our demo. As you can see here, David is on the device. I'm currently so he clips in just like so. It's very easy method. And then you just twist to get out. Super easy for the astronauts. They're already trained on this for the device. There you can see me changing the resistance to be easier for him so he's able to go faster. And you would be able to actually see and hear the valves opening and dilating to be wider. And he's hooked up fully to the resistance system there with the harnesses and the bungee cords helping to provide his load weight, although at the moment they're not in full tension that would simulate that because he is more simulating about 10% of his body weight. A big thank you to our faculty advisors and our NASA mentor, as well as to the people who helped us in the shop with building and designing all of this. We are NASA Space Grant. Thanks and gig 'em.
All right, questions?
So is this a one-size-fit-all device, or how does it work with people of varying heights and sizes?
Absolutely. So multiple people of heights and sizes, as well as weights, can absolutely fit this device. As I said earlier, there's multiple places in the wheel systems to be able to move up and down the handholds and footholds, as well as the harness is adjustable, and so are they each get their own shoes already for the cycling device, which is working in with the spinner wheel that they currently have. So we wouldn't be adding on any mass in that aspect, as well as it being personalized to each astronaut.
Great presentation, guys. The problem you're addressing is reduced cardiovascular capacity, right, for astronauts. And you put that in your title, physiological changes. So comparing your device to the devices that we already have, how do you plan to test the physiological data? Because your next future direction is looking at biomechanical data. So how can you say that physiologically this is a
So we plan to address that by doing studies like the parabolic flight. So this was done by NASA, I believe, back in the 70s, where they were first evaluating these resistive devices. So they've actually done testing with vertical climbers already using that method, and so they've evaluated the efficiency of climbing compared to other exercise. So we've tried to actually reach out to NASA to try and get that data from them. However, that's very, very deep, and they can't even find it. All we have is those photos that we found from another source. So we would like to do our own study if possible, but reaching out to NASA and seeing what they already have would be the next steps.
Other questions?
Is this to be used on Earth, or can you install it on the ISS?
So this is actually designed specifically to be sent up to the moon and Mars, because the current devices they have up there, such as the ARED and the treadmill, are too heavy to be sent on those long duration space flights. So this was designed for the idea of placing it in a space shuttle, for example, or even on the living systems there. And it's in the same system as a high beam, so you could essentially either build it in structurally, leaving a little bit of space on either side for the handholds and footholds, or you could also, we're looking into in the future making it a collapsible device and having the current pulley system being retractable and increasing in tension and decreasing in tension, so that way we can fold it into the same size that the spinner wheel is right now.
Thank you.
Just a subtlety you mentioned Mars and the moon, so zero G versus low G, did y'all take that into account, or was this designed specifically for moving gravity?
So this is able to be used on Earth as is right now, actually, and so we have looked into being able to use it on the moon and Mars. As we mentioned earlier, with a harness system in the base, you would be able to alter the amount of load that you place on your system based off of the amount of tension you put those ropes into, and you can also change the resistance values on here to make it more difficult or less difficult compared to whichever sort of gravity you're on. So maybe on Earth you'd like it to be zero resistance because it's you already have that extra mass resistance from the gravity acting on you and stuff like
All right, thank you, Agnes.
that. Thank you.
Okay, our next team is from University of Houston Clear Lake, and they are the Cosmic Commanders.
Lasky. I'm joined today with Isaac Beeman, Gerald Gay, Cameron Fassbender, and Brian Sharp. We are the Cosmic Painters from the University of Houston Clear Lake. Our faculty advisor is Dr. Billa, as well as our NASA mentor is Robert Muckles. And our design challenge this semester was the Lunar Surface Habitat Module. So jumping in, looking at the overall outline of how everything's going to be going, we're first going to jump into the criteria and constraints, both set out by TSGC as well as just standards set forth by NASA. Then we're going to dive into basically the design from last semester that we had and then changes from it. And then we're going to jump into the actual kind of meat and potatoes that involve basically making this, which is our prototype, if you will. And then jumping into the final design as to how we would build the full-size habitat and then concluding it all out. Jumping into the actual criteria and constraints, it's going to be first the constraints set forth by TSGC, first being the actual mass itself, basically making sure it is light enough to basically be able to be put on a rocket and sent up to the moon to where it's going to reside, and then have a comfortable living area between 50 to 80 square meters, just so it's big enough for a crew of 4 to 6 to live comfortably in it, and then be able to survive the thermal fluctuations on the moon itself, and then be able to protect itself from the cosmic radiation coming from the sun and various other areas in the outer space. And then we are taking one assumption. We are assuming there already is a nuclear reactor there on the moon. I know NASA and the administration wants to try and put one there by 2030, especially with the new lunar base that we heard about last night. I'm sure that is pushed up a little bit. Then jumping into the actual standards itself, these are not all of them. These are kind of just the big ones. They obviously kind of break down more and more. They range from crew health to the materials that we are using to power and thermal systems, safety, as well as the radiation and environment of the habitat itself. But then jumping into the actual last design from last semester's design will be Cameron.
So for our habitat, the central component is the pressure hole, which is on the elliptic cylinder design, which just means it's a cylinder with ellipsoidal heads on the end. Cut into the cylindrical face is an iso-grid, which provides some savings without reducing the structural rigidity. Our habitat is split into 2 levels. The lower level is primarily meant as a laboratory space, and the upper level is meant as living quarters for our crew. Covering most of the exterior of our habitat is our whipple shield, which provides protection against micrometeorites, and it also reflects most of the incident solar radiation in the form of visible UV and infrared light. And we also have a deployable ramp on the front of our habitat that I'll talk about in a minute. On the lower level, we have a airlock, and it's a double chamber design, which provides space for our astronauts to remove most of the regolith from their spacesuits, and also to provide a cleaner area for them to take off and put on their spacesuits without trapping regolith into the habitat. One of the key components of our habitat is our rotating radiation shield. We have to provide a protection against the cosmic radiation produced by the sun, and so to do that without having a large amount of weight, we have a rotating radiation shield design that moves within the walls of our habitat, and it constantly puts itself in between our astronauts and the sun. And then we also have 4 extendable legs that are collapsible. They have crushable aluminum for shock absorption during landing, and they also have a jack screw on the end so that the habitat can be leveled after landing. Our habitat weighs 13.6 metric tons, and our total payload is 45 3/4 tons, which is just under the weight limit for our chosen launch vehicle. Some of the design changes we have made since the last time we were here, we didn't fundamentally change any of the major components, but we did add a support ring for our lander for better weight distribution during launch, and also it provides a secure attachment point for the sky crane. We also refined our ramp design and fully developed it so that it articulates, and it's deployable to the astronauts with their electric drills. And then we also refined our radiation shield design with locking bars to each of the shield pieces so they don't move when they're not supposed to, and the electric motor to move them autonomously. And now Brian will talk about prototype.
Thank you, Cameron. For the base of our prototype, we searched for something that was cheap and readily available that we could adapt to make these for our needs. And due to the semi-ellipsoid top and bottom and cylindrical nature of our design, the natural choice was a tank of some sort, whether it be a storage tank or an air tank, and luckily we were able to find a cheap and broken air compressor tank, as you can see here, and we were able to use that for our needs. And in the design of our prototype, we made the determination that it would be the best course of action to split it in two so that the prototype can open up and show the interior designs that we made on the inside. And to do this, we used a laser level and an angle grinder to make a vertical perimeter cut around the entirety of the tank. And once we opened it up, we noticed that there was a lot of scale and corrosion on the inside due to it being used. And additionally, there was paint on the outside. So to prepare for future grinding and welding, we sandblasted the entirety of the tank. Our prototype itself is 1/15 scale, and the tank was 16 inches in diameter, which perfectly fit that scale. However, the height of the original tank did not fit that scale. It was too big. So to remedy that, we did another horizontal perimeter cut and took a cross-sectional cut out of the tank. You can see it there in 4 pieces, and then used MIG welding to weld it back into 2. Following that, we ground down the exterior surface of the tank to get that nice surface finish, and welded on hinges and latches, as you can see on the final product, and here in figure 21. And this is to facilitate the opening and closing function of the prototype to show off the interior. And to talk about the interior, I'll now introduce Gerald again.
Thank you, Brian. So in creating the inside, we used trade interior floors. They were made out of 6 pieces of sheet metal. They were cut into semicircles, and to attach it inside, we used MIG welding. So you can see the half circles in figure 23, and the MIG welding process in figure 24. For figure 25, we had to repurpose some of the metal to create additional floor. So in doing so, it did bend. So once it was welded, we had to utilize an arbor press to straighten it out. And we were worried about burning through our pressure compressor, so we had to, instead of welding full beads, we tacked the insides. And I'll give it over to Isaac.
Yeah, so for our legs, they're custom fabricated. They're spring loaded on the inside. On the actual lab, they have crushable aluminum honeycomb, but for our design, it's got the springs on the inside. So what we used is steel tubing. We had to turn it down on the lathe a little bit. And then we used steel rods on the inside to be guided through that. We also welded on swivel feet on the bottom for uneven terrain, as well as the brackets themselves. We used square tubing and welded that onto the prototype. So the ISO grid itself, that's the triangular portion of the outside of our prototype. We used expanded metal, which is very similar to barbecue grating. And naturally, that metal is shaped like a diamond, so we had to make it into triangles. So the way we went about that is we used 9-gauge stainless steel wire and cut it to size and put that individually in each diamond and then tack welded it in. So it was a lot of welding. Additionally, we had to obviously cut and bend that barbecue grating to fit our pressure vessel. So we ground those down to make it flat on the outside. And as you can see in figure 30, that's what it looked like as we were constructing the ISO grid itself, so that was in progress. And then figure 31 shows us grinding it down. So it's a lot of welding and a lot of grinding. Something we learned is rapid cooling during welding will cause cracking, so we need to make sure that we take that into consideration. For some of the other accessories that we have 3D printed parts, like our door, as well as the ramp itself, and our sky crane attachment, radiation shields on the inside as well, on their tracks. So for our final design and assembly, these are some images if you can't see it up front. So we have perspective view. We also have a scale model in figure 36. That's a 6-foot person standing at the front door, and then you can see the inside radiation shielding. I'm going to hand it back off to Gerald to talk about the actual production of our lab.
So producing the pressure vessel, the 2 processes will be CNC and ice to achieve the ISO grid structure, and to form it into the shape it is, we use the rolling process. And of course, it's going to be using friction stir welding to join all the pieces of metal. This is also used for the Whipple shield and the leg attachments. And any type of welding process will utilize a post-weld heat treatment for stress relieving. In conclusion, the lab is geared towards long-term habitation on the lunar surface, but could be used for Mars and beyond. The design design would make realistic math considerations based on the current capabilities, and in the future, we want to reevaluate potential mass-reducing concepts. Thank you. These are references and questions.
Questions?
If the motor that moves your radiation shield fails, can the radiation shield be moved by hand?
Yes. Yeah, so it's like similar to how your garage door is. If your house doesn't have any power, you can basically just pull the pin and move it just like a garage door.
Thank you.
Other questions?
For manufacturing, I saw a lot of, I'm gonna say, old school, like welding and stuff. Where has 3D progressed, or why can't we make things 3D, or I forgot what they call it these days, additive manufacturing?
The real one or the prototype?
Both.
So for the prototype, we wanted a full metal model, one, twofold, one to test our manufacturing skills, and two, just so it can be sturdy, and just designing the whole thing, printing the whole thing in one piece, doing it would just kind of be hard. Now, in terms of the actual lab, stuff like SLS printing, titanium, it's still not a fully mature technology, I'd say, in terms of like layer adhesion, things like voids, cracks, porosity. Those are all considerations that you have to think about when considering additive manufacturing. And something like this, if you're living on the moon, that's just a big risk. So go with CNC, friction stir welding.
Other questions?
Now that you have a model, is there any kind of testing that you could do with it?
So our model is steel, so it's not going to be exactly one-to-one same results. We do plan on doing FEA thermal simulations on what it would be like on our CAD models, but most of our semester this year was spent on just making that. So we could test that, it just wouldn't be the same as if we use the actual aluminum we plan on using the final model.
To add to that, we did email the company that makes our aluminum, Constellium in France, asked for anything, scrap, anything, and we didn't get a response. So we wanted to do something, but yeah.
Okay, thank you, team. Okay, our next team is from Texas State, and they are the Rad Dogs.
I'm Brian, I'm the project manager. We have Sam here, Stuart, and Hunter. So what are these four handsome guys doing? Basically, we're connecting the dots between two things that NASA wants to do. One of them is upgrade the radiation tolerant chip that they're currently using in space. Right now they're using what's called the RAD 750, which was launched in 2005. And so it's pretty slow compared to modern chips. So NASA's trying to upgrade to microchips HPSC, which is much faster. At the same time, they're also trying to use a different laptop architecture in space. And they're moving to the Framework 16, which is a really cool modular laptop because everything in it talks to each other using USB, so you can change out the parts. The problem is that the HPSC talks to everything using PCIe, and the Framework 16 talks to everything using USB, so you can't plug them into each other. So basically what we're doing is we're designing a PCIe to USB host controller. You plug the HPSC up in at the top, it goes through our PCI 11400, which is like the traffic controller for the data, and it goes down to the laptop, basically allowing us to use that HPSC in the laptop. So we split our work into 4 subsections. Hunter is doing the processor integration. I did the PCIe Express. Sam is doing the USB functionality, and Stuart is doing power.
So the process integration is really just getting this PCI 11400 to work with everything else, right? So we have this PCIe to USB connections that will function and allow us to use different components on the Framework 16. So that processor is going to need a signal. It's going to allow for it to synchronize and reliable operation. Then we're going to have multi-lanes, so you can see that the PCIe will have enough lanes to support high-speed capabilities. There's capacitors and resistors all around, so these are going to help with power decoupling, stabilizing, signal integrity, and EMI, or electromagnetic interference. The processor does support USB-C and USB-A that you're probably familiar with, and Sam's going to talk more about that.
So to talk about the USB subsystem, I want to first direct your attention to our high-level block diagram for the overall laptop design. You'll see in the orange circle our PCIe to USB host controller. Supported from our host controller are 4 downstream USB hubs. Those are in the red circles. And those will take the USB ports that we provide and expand them to cover the full necessary range of USB that the framework design needs. Now to talk about our block diagram specifically, we support 2 USB-C Super Speed Plus USB ports. These are non-reversible. That's an important design decision I'll cover in a second. And then we also support 2 USB-A high-speed ports. So going back to those USB-C, let's just take a second to talk about the typical USB-C pinout, because this will help to inform our design decision. In the diagram on the right side of the screen, you'll see the PCI 11400, and it supports 2 Super Speed Plus physical layers. And what that means is that natively, the PCI 11400 can only support 1 USB-C port. And the reason why is because of this, the pinout right here. You'll notice that the USB-C pinout is 24 total pins. It's 2 sets of 12 pins, and each set is the mirror of the other. And the purpose of that is purely for the reversibility, so it's for the user. But what happens is you need to send 1 physical layer to one side and 1 to the other side. Since we only have 2, that means we can only support 1 USB-C port. That was a problem. So what we can do is, if we remove half of these pins, we're able to then to send 1 layer to one port and 1 to the other, and that gets us the 2 USB-C ports that we need. Now this is really important. You might be wondering, well, why would you remove the reversibility of USB-C? That's one of the big selling points. Our design is for the context of a motherboard design. And in no motherboard design would you use all 24 pins. Instead, you would only route 12 pins, because at any given time, you would only use 12 pins anyways. And if you don't have the physical port, then you don't need all pins. And so this design decision really really contributes to the final design. It's very reflective of it. And it also simplifies the design a lot. In order to support the full reversibility, we would have had to include a variety of other integrated circuits as well. So this just simplifies everything.
So I did the PCI Express. It's pretty cool. It uses a layering system to transmit data. At the lowest level, there's a physical layer that is just a pair of bidirectional wires that transfers the signal to the data link layer, which transmits TLPs, which are transaction layer packets, to the transaction layer, which is the topmost layer of the PCI switch. It's pipelined, full transaction protocol, so it's super fast. Basically, it can do things in parallel, and that communicates to the root complex of the software, which is external to the PCIe. That's whatever you're trying to talk to. To configure the board, we use EEPROM, which stands for Electronically Erasable Programmable Read-Only Memory. Similar boards use stuff like Macrobus and UART, but we wanted to do just EEPROM because it's much slimmer and it does exactly what we wanted to do, so there's no reason to go outside of that.
The role is to deliver power to everybody else's subsystems. So Brian's work on the EEPROM and the PCIe integration, and then Sam's work on incorporating USB ports to the processor that Hunter integrated with everybody else's stuff. All of those components require voltage and a current source, and they also chose integrated circuits that make their subsystems functional. All of those integrated circuits also require voltage and current sources. So this is just a high-level overview of how I'm delivering power to everybody else's subsystem. You start with a 12-volt external source, or just a source from the PCIe or from a motherboard that you can plug our board into, and then that gets converted into a 5-volt source. Every red box that you're looking at is an integrated circuit that I chose that meets the voltage requirements and also exceeds the current requirements for everybody else's integrated circuits and supporting systems. The 5-volt source gets converted into a 3.3 volt source, a 1.1 volt source, and then a specific 5-volt V-bus source that is specific to USB ports. And everything that's in blue on the right-hand side is everything that I'm supporting with my integrated circuits and power delivery. And Brian's now going to talk to you guys about how we took our ideas and used those ideas to design a printed circuit board.
Yep. So over the course of 2 semesters, we put a lot of hard work into this. Most of what we're doing was creating schematics. So we made 6 pages of schematics, which you can see on the board here. And we also created the layout this semester so that you can see a 3D view and a 2-dimensional view of all the stuff that we did. This would not have been possible without the help of our tremendous faculty and sponsors. So we just want to thank Justin Bautista and Mr. Jeff Stevens and the Texas Space Grant Consortium for making all of this possible. Any questions?
Question?
So I don't really understand circuit boards that much, but on y'all's diagram, the upper right-hand corner, so is that just empty space that can be optimized, or is there a point in having all that up there without, I guess, any components?
So we made the board outline before we started routing it, of course. So we didn't know how much space we were going to need. It's a 6-layer board, so we were able to make it a lot denser than we previously expected. So we did put our logo there. That's our optimization.
Other questions? I'll get my steps in today.
I'll make it easier. Could you go up one more slide, or go back one more slide? I'm sorry, keep going. All right, so here on the right, you said that these are all of the things that we can plug into it. What kind, if I'm using all of those, is that still going to be okay with power?
Yeah, so I actually designed, so the main voltage supply is the step-down power supply, so it actually can supply up to 8 amps. Everything that's in blue on the right, I think it only pulls around 4 amps. I think it was actually 3.9, but 4 amps. And also I chose that specific integrated circuit because it is extremely stable. So even if you do have a large current spike because you just switched everything on, you're not going to get this terrible shutdown of everything. So
excellent, thank you.
So I think one of the big concerns is the radiation tolerance. Is there anything about these circuits or the chips you're picking, or what are you doing for the radiation tolerance?
concept to allow us to put a radiation tolerant chip into this laptop. Our design itself is, that's more of like a materials thing. But our design is mostly just allowing USB to talk to PCIe.
Any other questions? All right, thank you, team. Oh, one more.
Is there any coding involved in that transfer, or is it all hardware?
Do a little coding for stability stuff, but yeah, did you guys do?
No, we did. It's almost entirely hardware. So what our design is hardware. All the software stuff is like what it's going through our design, but we're doing the hardware of the design.
Yeah, just did MATLAB for simulations. That was it.
Okay, thank you.
All right, thank you very much. All right, our next team is from Texas A&M Kingsville, and they are the Farscape Engineering Company.
Good morning, we're Team Farscape from Texas A&M Kingsville. I'm Connor Anderson, the team lead. My teammates are Kyle Cavazos, William McBrayer, Marcus Martinez, Diego Regalado, and Zachary Davis. Our mission is to design a machine that's going to bury fiber optic and power cable on the lunar surface. We're doing this in service to NASA's greater goal of the moon base, long-term human presence on the lunar surface, and for that we're going to need a communications and a power network. Using our research as well as our mentor's guidance, we came up with a 1 meter depth to protect our cable. We've set our maximum mass at 160 kilograms to ease our delivery to the lunar surface. Our operational life, we're shooting for 10 to 15 kilometers of cable buried, and we believe that we've exceeded that quite a bit. The blade and cable cartridges will be reloadable for easy operation, longer service life, less moving parts. It's going to be remotely operated, so we don't have to have an astronaut physically driving the machine, because that would be a horrible job for them. We're using a drivetrain that's going to help us remain stable and give us enough torque to drive the machine during cutting. And our machine is rechargeable with an available nuclear generator, which is one of our assumptions.
So the lunar environment is the main thing that makes this project different than anything on the Earth. The regolith is made up of fine dust and rock fragments that are extremely abrasive and electrically charged from UV radiation and solar wind. And because of the charge, they can stick to the equipment and cause damage. The density on the regolith at the surface is 1.3 grams per centimeter cubed, and it increases with depth. So at our 1 meter cut depth, the density is going to be 1.83 grams per centimeter cubed. If we found these in the equation there. Gravity is another important thing. It's around 1/6 of that of the Earth, so that's going to be affect our weight. And if any dust does get kicked up, it can get to our components. Extreme temperature change is was our main focus for material selection. It goes from negative 130 degrees Celsius up to 120 degrees. Because the lunar environment, we chose to go with the vibratory plow. Uses a long slender blade that extends off the front of the machine and uses a low frequency and high amplitude vibratory shaker box to shake the blade and make it slip to the soil. Reduces resistance from the soil, and the cable can be laid at the same time while you're cutting, and it doesn't disrupt the surface as much as a chain-driven ditch witch style, so it requires a little backfill.
Now, continuing on the blade, how did we design this? So, starting with inspiration from blades already used here on Earth in similar environments, sandy, silty soils, using that as kind of a baseline to get a general shape, then continuing on from there. So, what we ended up with was a final length of 1.35, gives us about 5 centimeters of clearance from the top of the regolith to the bottom of the block that it will have. The thickness is 1.27 centimeters. That is a hair thicker than the widest diameter cable that will be laid down. Since the cable is underneath the regolith, it does not need to be insulated, so it can be a lot thinner. So it doesn't have to be a super thin, thick cable. The width from the cutting edge to the spine is 0.2 meters. That's a good width to have good surface area to push the dirt onto the sides as it is moving forward. Cutting was set at 24 degrees. That is an angle that is an industry standard used here. That was found to be good to limit the moment of the arm on machines to prevent the machines from tipping over too much and not requiring as much of a counterweight. Bevel angle, which is the cutting angle of the front of the edge, is at 40 degrees. That is a wedge shape that helps move the regolith to the sides as this moves forward. And the tang, which is the spot at the very top of the blade, that is 0.3 meters. That is meant to lock it in place. The lock system is also down there in the bottom left corner of the screen. So the blade comes up and locks into that lock bar, which is then with an actuator pulled forward, and it locks the blade to the front of it and prevents it from rotating. Now, iterations, it first started off as a solid blade that would be welded in place. That's 6 centimeters thick. That was found to be far too thick for what cables are going to be laid. So that was thinned out, and then we wanted to make this replaceable because that blade would limit the lifespan of our machine. So making it replaceable means that we can get a lot more life out of this machine and not have it be limited to only a single blade. We can now have multiple blades used to be manufactured and then replaced as they break and dull out. And then here's a material matrix that we used for the blade. We use this for all other components as well. And we chose density, strength, hardness, both Breno and Rockwell, one for just strength of the material and also one for abrasion resistance. So we did choose a steel, which is very heavy, high density, and it was, high abrasion resistance, and because it is steel, the blade is going to be actually hollowed out to reduce weight as well.
Since we already talked about our main mechanism uses vibration, we would like to control vibration as much as we can internally. We have sensitive components such as electronics and also battery connections. We figured, and we also researched, there's these things called sandwich mounts. If you don't know what they are, they're diameters that can be put internally into components or connect to a component and a body. This one that we researched is a high temperature silicone rubber. It can be put inside our arms, or we can put it between our arms and our body to dampen as much as we can internally. This one specifically has a duality 68 hardness and also has a temperature range from -80 degrees Fahrenheit to 300. And one of the subsystems we are using to move this machine is a Caterpillar track style. This has a high efficiency in sandy environments, and this one specifically that we designed uses electric motors, specifically one you would find on most electric cars. That is the same type. It uses a 4-to-1 gear reduction to improve traction. The track links each have hexagonal pegs so that they will reduce weight and also improve traction by digging to the ground and hopefully dropping off, not kicking up much dust. We also chose 2 different materials. ALMS95 is a NASA-made material. This is a high here to read. This is a lightweight, high tensile strength alloy that will hopefully give this movement system a long track life and also not wear down as easy because it has a very high abrasion resistance. The 7050 T765 is used for the rollers. This one doesn't have as high abrasion resistance, but has a higher tensile strength and also has a high temperature strength, so it should last a lot longer for the rollers.
For the frame, we use the square tubing because it provides high strength while still minimizing weight, which is important for the harsh lunar terrain. The frame has mounting points for the robotic arm, the tracks, and the panels, and internal components. This is our complete rover assembly. This design has our protective enclosure, our track mobility system, and our robotic plow mechanism with our electronic housing in our structural frame in one whole system, and every part was designed to work together while still having the rover compact and durable.
This is our finite element analysis of blade. The properties we use were all of the lunar regolith properties found at 1 meter depth. The first image you see is the von Misses. The second one is the frequency analysis. For the von Misses, the max force we're going to get is well within the yield strength, and the cutting force we use for the blade is going to be just 336 newtons. On the next slide, we have some more finite element analysis of the other main components we use. One of these is drive roller, the other one's the blade and lock. Both of these, once again, are well within their yoke strength. So this proves that all of our parts will be able to perform under the conditions we need in order to get the job done. Some future work that we hope to accomplish are to continue and complete prototyping. We want to complete the detailed design, which includes machining tolerances and other manufacturing specifications. This is important because we need to satisfy all the ABET requirements, because this is also our senior design project. We would like to have some acknowledgments. We would like to thank our space grant advisor, Mr. Lansdowne, over here, our senior design professor, Dr. Grady, our faculty advisor, Dr. Peel, and the rest of the Texas A&M University Kingsville staff. These are references. Any questions?
Good morning. You mentioned a lot of work about the regolith, how you're going to go through it. On the surface, it's made of different sediments. So not only are you going through regolith, you're going through lava sediments, you're going through different types of material that's not really known. Have you looked at that application, not only regolith? My second question to ask you is, you did a lot of work on the components of the blade, but then you mentioned you have electrical motors and so forth. Have you looked at the hardware and the driving force of that hardware? Because if you have a solar flare or cosmic ray that can affect and shut down your vehicle completely, it doesn't matter if your blade's top of the line. If you have no driving force, you can't use it. So have you looked at applications of how to strengthen the driving force, which basically means the motor and so forth?
Well, first, as for the regolith question, that was the predominant thing that we looked at. The truth be told, we really don't know what we're going to be cutting through in the area that we're at. And that's something that NASA would need to look at during their surveying. We do know that we can handle most environments that are similar to regolith, as far as like gravel, sand, that would be fine. Where we would run into issues if we had very large obstructions that were in the subsurface that we can't see. And our machine really doesn't know a way to see that. The only thing we can do is build its fail-safes to halt operations in case, say like the holding torque on the robotic arm was overcome, that it would stop and then the operator could work that problem. As for the electrical components and hardening, I don't really know all that much about that. We're all mechanical engineers. We haven't looked at that thoroughly. It's something we've thought about as an issue, but we just haven't been able to put much time into that specifically.
Sort of follow up on the environment, I was noticing in terms of different materials, you know, and one of the environments is temperature extremes, right? So with all these extremes and dissimilar materials, I don't know, with expansion and I don't know, is that something you might think about and try to have some similarity? Otherwise, you might run into binding problems and things like that.
Yeah, that is a big thing that we thought about. A lot of our materials are low, they handle thermal expansion really well. They don't expand or contract too much. And we are going to have some, that's something that comes into play with the tolerances that we mentioned that we're currently defining. Yeah, that's a big thing for us. And we wanted to make sure that all of our parts were going to still work at temperature extreme.
With that as well, we were also informed that we most likely only be operating during the lunar day and not during the lunar night. So it'd be put away or stored during the lunar night, and then this machine will only be operated during the day. So we don't have the high temperature extreme. We wouldn't have to have materials that could withstand the very cold and the very hot. It'd mostly just be on the hotter end of the, for the operations.
Your original design that came, that's earthbound, has a pretty significant weight. What's the weight of yours, and what's it going to be like when it's on the moon, and there's a lot less weight to be able to drive it that long near the ground?
So we are shooting for 160 kilogram total weight for this machine. Now, the machines that are used here on Earth, they are a bit heavier and they do have a lot more counterweights to them. We don't have to worry about that as much because the forces actually acting upon the blade are fairly low. Statically, we are looking at about 8 newtons of force along the front edge of the blade with a 10 newton meter moment against that arm, and the arm and then into the frame and the weight of the battery will counteract that tremendously. That is not really an issue. And then our side to side is 40 newtons on the side of the blade to push into the arms, and that is where our damping system will take care of that force. So the weight of the machine itself does not have to be very heavy because we're actually not using a lot of force. We're not going against a lot of it because of these soil density here being very, very low.
One other thought here. During the Apollo program, the astronauts were asked to drive some stakes into the ground, and they found that after a few inches, it started binding up. And part of it's due to the abrasive nature, how the particles cling to each other. Have you been able to do any testing to demonstrate that this kind of blade is going to be able to penetrate there, considering that it's not rounded soil, not what we have?
We haven't been able to do any testing, and it really just comes down to our production capabilities for the prototype. The way our blade's designed, it's really hard to manufacture for us as students. But that is something that we're looking into. We want to do that for our full senior design. The other thing is simulating lunar regolith is a little bit tricky. Supposedly our department has some floating around somewhere. For the simulation.
50 bucks a kilogram, so yeah.
Yeah.
It's not a lot of it.
Yeah. But yeah, that is something that we want to do. Because we really want to validate this design. We have a lot of faith in it. And it just comes down to what our restrictions are.
Excellent. Thank you.
All right. Thank you, Farscape.
teams. A round of applause again. We'll take a short break and be back at 9:15 with the next section. First up, we have UT Tyler, Team Astroverse.
Morning, everybody. So we are Team Astroverse, and we've been tasked with designing a rover for exploring the Psyche 16 asteroid. My name is Juan Hernandez. I'm the team leader. My teammates are Armand, Gerardo, and Kareem. We'd like to also thank our NASA mentor, Dr. Casey Bowman, and our faculty advisor, Dr. Frico. So I'll go quickly and give you some background on the asteroid. My phone's right here. So the asteroid is very rocky, uneven, has a little bit of a semi-metallic ring, high exposure UV, low gravity, and depending on its orbit, its temperature range can fluctuate very significantly from -700 degrees to 7 degrees Celsius. And I'm going to let Kareem go over our model.
So this is our base, our modular rover chassis, and it's built from aluminum 6061 with a 1.5 inch square tubing, and it's a lightweight, and it's easy, allows assembles for all the parts and accessories. So this is our intended Psyche. This is our intended rover Psyche for the space application, and as you can see, it has camera, solar panel, and LiDAR sensor that allows to navigate and capture obstacles. And as you can see, it also features aluminum wheels on an improved surface. And for our rocker bogie suspension system, it is designed to be balanced mobility and improve ground contact. So moreover, it improves the stability and allows the rover to navigate on an uneven surface.
So everybody's pretty familiar with the rocker bogie suspension system. A lot of rovers use it. What makes ours kind of unique is they either use differential plates or differential gears. However, ours has the differential mechanism within the chassis. Usually they put them on top of the chassis or on the bottom. We put in the middle. This gives a better center of gravity, better balance. We get better ground clearance, and because this thing is also designed to take payload, we have room on top now. So the twist to our project is, since this is our senior design project, our department asked us, like, hey, how can you make this rover modular, or how can you modify this to where it can be used here on Earth at the same time? So with just some quick, simple changes in material, you can, like the wheels, you can also make this here usable here on Earth for different applications. So prior to us constructing any of this, we did simulations. This one, most important simulation, basically how this rover is going to behave over uneven surfaces. We did this through SolidWorks. This is a very simplified version of it. But what we got from here is how fast it's moving, our center of gravity is positioned, things like that, and most importantly, we're tracking our body's pitch and roll.
Yes. As you can see, all our rover is made from raw material, and we use our own hands-on experience to build everything. On the first picture, you can see us doing some aluminum welding, and the other picture, you can see Joanna and me doing the assembly of the chassis. Okay, this is the integrated modular chassis of the rover, and as Karim was saying before, everything is made from aluminum 6061 from its lightweight and from a high strength. The high strength because we wanted to ensure the load distribution across the six wheel of the six wheel. Also, we have the differential plate that ensure the good mobility of our rover, and in the front of our rover we have our electronic component. In the electronic component, we have the 24-volt battery, as you can see. We have two TB6600 step driver motor that drive the two-step motor in the front, and also we have two Cyclone 30 amps motor driver for the four DC motor in the back. Also, we have for the controls, we have the ESP32 for the Bluetooth connection because everything is working with the remote. And for the safety, we have 4 fuses, 4 30 amps fuses, just for safety purpose.
So we conducted a mobility test, and with that test, we validated the rover tilt's performance to be stable. And we placed one of the, on the left photo, we placed one of the arms on top of a 22-inch stone. And after, if it goes any higher, we concluded that it could become unstable. And the good thing is that since we're controlling it with a controller, and it's not autonomously navigated, then we can stop whether, if it goes too much and it becomes unstable, then we stop and reverse back. And we also conducted a roll angle testing with a maximum speed of 3.2 miles per hour, and that's with no payload. And with that, we went down some steps to see how stable it was with any payload on it. We also conducted a payload testing. As you can see on the left photo, our team leader Juan is on top of the rover. He weighs around 130 pounds. It's to make sure there was no buckling or any deformation. And on the right photo, we placed a toolbox of 60 pounds on the rear end of the rover to conduct the payload testing on the differential mechanism to see whether the mechanism would bend or any deformation would happen. Here's our final prototype of our rover. As you can see on the right side or your left side, there's a cover on it to hide any imperfections or hide the electronic components. And right now we could demonstrate you a quick setup of it going forwards and backwards with the controller.
So many of you have came by our poster yesterday. It's actually very easy to turn on and use. We have a hidden switch right here that turns the entire system on. You connect your controller, it takes a couple seconds to connect with Bluetooth. After that, the controls are pretty simple. Forward is forward, backward, backwards. So since we have limited room, I'll just go real quick here. Takes a couple seconds to connect.
For our project expenses, we had a total of $1,360. That includes our raw materials like the aluminum with $600, our electrical components as $560, fasteners and hardware $80, and wheels and miscellaneous $120. And we were given a budget of $2,000 with a saved amount of $640. That concludes our presentation. Thank you, everyone, and we'd be happy to answer any questions.
Questions?
Hello. Why did you choose a 6000 series aluminum over other stronger options such as aluminum 7000 series or a 2000 series?
So we chose 6061 mainly because of its lightweight and strong durability, but also because of its affordability too. Like we looked into 6063, but it turns out that was actually not very well with high load applications. So there's that too, and because the 6061 aluminum also has a high tolerance to corrosion.
Hi, I was wondering, were you able to do any payload testing while moving up and down steps and vertical areas such as that to be able to simulate going over rocks and such?
So we had that plan, we just didn't get the chance to conduct it. So if you see these T-rail slots on top, that's actually so you can secure some payload onto it. Obviously, we could do it with me on it, but it's, I could fall off because very jolty controls right now. But yes.
So I noticed that for your drive, you're doing direct drive directly from the motor to the wheel. Did you have any issues going over like trickier terrain, like protecting those motors, or were there any thoughts about potentially adding like an extra gear mechanism or transmission, or is that just too complicated with the
No, we did have something planned in mind. So our 4 DC motors are fine when they're high torque spec motors, they're planetary gears. However, our front 2 steering motors are not directly powered. Those are mainly just for steering, but if you notice that they tend to wiggle a little bit. That's after like continuous testing, they wore out a little bit, things like that. So something we would like to improve on that is either get some bigger spectrum motors or convert them to be a direct drive, just like DC motors. So we either get a bigger spectrum motor to have higher holding torque and keep it straight.
So I saw that you had a great interface control system. You have to remember the astronauts are in a tight air suit. The user interface between the remote and the hardware, did you take into consideration the gloves are bulky, clunky, so using that type of remote will not work with their bulkiness of the gloves? So you guys might need future work is to look at the interface of that remote control and to be able to do with the suits on.
So we didn't look that far into it, but we did look into making this fully autonomous by adding a LiDAR system. So just like how we showed our other model of it for Psyche application. But I guess it comes just down to a quick tweak to our Arduino program to make it fully autonomous.
And also we chose to do that because this is the Earth application version. On the space application, we will be using the LiDAR to make the rover very autonomous. But on Earth application, the remote is something easy to make and we can use it easily.
Do you guys know what the gravity is on the Psyche?
It's very low. It's, I believe, 0.14 meters per second, something like that. So it's less than the moon's, yes.
Right, so it's about 0.2% of what Earth's gravity is. That seems like a difficult number. I mean, that seems difficult in terms of using a traction-based wheels. Did you guys have thoughts on that?
So originally we did, and that was because we were originally planning to use tank style steering. But with the way to get the prototype set up, that would be actually very energy inefficient, especially when you have rubber wheels, things like that. So for the space application, that could be considered.
All right, thank you, team. Okay, our next team then is Texas State Rantopus.
Hello, I'm Cameron Gillis. I'm the student project manager for the team Rantopus. Over here, the beautiful Fatima. She is the device configuration testing lead. Matthew Giddens is our USB communication PCB layout lead. And Javier Garcia is our power subsystem lead. So quick agenda. We're going to run through a background of our device. We're going to give a quick overview of the effects of radiation on devices because we got a lot of questions about that yesterday. Then we're going to run into design philosophy, give quick overviews of different aspects of our subsystem. We'll walk through a preliminary validation and testing plan, and then we'll give a closing summary and acknowledgements. And for the background, just to start off, I'm sure you all heard about the Outlook fiasco with Artemis 2, but there's also a personal computing device that was bricked when they were passing their radiation belts. It doesn't mean that radiation killed it, but correlation is there. So NASA wants to help develop a user-friendly, efficient computing device for crewed missions into space. They partnered with Microchip to create the PIC64 high-performance spaceflight computer, which is a radiation-tolerant vector processor. They're also looking at the framework laptop ecosystem to create a modular and possibly in-situ repairable laptop. Prior teams, we're the fourth iteration of teams from Texas State University. Prior teams have defined high-level system architecture, and then you saw Raddox present earlier. They've designed the PCIe USB host controller that will let the PIC64 talk with USB devices. This is critical because the PIC64 does not have onboard USB communication features. So the Framework 16 almost exclusively communicates with devices through USB. So we have to route 16 downstream connections to now 4 upstream connections. And our work is to develop a USB hub development board to prove out the concept of how we will make those connections. All right, give a quick rundown of radiation specs. First, I'm going to give you guys a quick down and dirty example of a transistor. A transistor can be conceived of as an electrical switch. On state, off state. There are 4 terminals on a transistor. We're going to talk about 3 today, just to keep it simple. You have the drain, the source, and the gate. Current travels from the drain to the source by a voltage differential applied to the drain. You also have a gate. Voltage applied to the gate either turns on or turns off the conducting channel. Now, radiation can affect these devices in many ways. When a high energy particle passes through the silicon lattice, or any crystalline lattice, it can effectively rip electrons from their host atoms. This can impart a current where you don't want one to exist, or where one shouldn't exist. It can also displace atoms within the lattice. And sometimes in insulators or places where you shouldn't have any current flowing, it'll permanently displace electrons. So in digital design, so for all right. So for digital design, you have high signal, low signal, ones and zeros, right? And when you interrupt current flow, you can make a 1 look like a 0 or a 0 look like a 1. That'll put glitches into the system. It can break your whole system. We don't really know, cascades can happen. You have also have, let's say you have the device in the off state. So you don't have a conducting channel. In the diagram, the conducting channel is blue. In the off state, that's not there. But over time, if you ionize out the insulator at the gate, holes will travel to the surface of the conducting channel. Those holes give a path for current to travel. So electrons can hop from hole to hole to hole, and basically you leak current in the off state. And if you have enough holes, it will just be on. Furthermore, in the off state, you have an event of basically called a single event latch-up. This is when you pass current from drain through the body to the source, bypassing the channel altogether. And you can pass extremely high currents and you can basically burn out your metal interconnects and you permanently disconnect the device. So that was quick down and dirty on radiation effects on semiconductors. Matthew?
So these are some device constraints that have affected and influenced our design choices. As he just talked about, radiation is a big one. For that case, we cannot eliminate the risks of radiation, but we can limit the components that are susceptible to radiation. For that, we choose analog components over digital as much as we can. It's not possible everywhere. We're making a digital circuit, but where we can, we choose analog circuits. We guarantee high signal integrity. It's a communication system. We need to guarantee that we are capable of passing a high-speed signal reliably across our device consistently. We want to ensure that all of our USB channels are correctly wired and are capable of passing those at high speeds. Thermal dissipation. It's always an issue in space. Luckily, our device is not intended to be used in a vacuum, but there are still thermal considerations to be made when a device is being sent to space. That primarily is an issue with our power delivery system. That is the system that will heat up the most. Our communication system produces a little bit of heat, but it's not so much of an issue. And as Cam mentioned, we are the fourth team to tackle this project, so we really want to support the follow-on developments. We expect many more teams to come on this project. We know that our system is only a small part and will ultimately be integrated into a larger system. So for that, we take a lot of choices to record what we're deciding. All of our component choices are recorded with our justifications to make component selection in the grand scheme of things much easier for people who are integrating our system. This is a scary block diagram. In the middle is the processor. That's beyond our reach. It's still being designed, but that will be the big red block. That's the core of the CPU. Right beneath that is the Rad Dogs, what they've done. Sorry, getting an echo. What the Rad Dogs have done, the PCIe to USB integrator. And the two larger blocks on either side, those are our USB hubs. So you can see that there's two of them. We'll be ultimately fed 4 USB inputs from their device to feed 16 total USB outputs along the laptop. This is the block diagram of just our development board. As you can see, we decided to only use 2 inputs and 8 outputs. It's for ease of prototyping and ease of design in our sake. We will ultimately duplicate the board and mirror it on either side of the device, so we will have 4 inputs and 16 outputs, but both sides will be identical in the devices that they have on them. In this, you can see our USB hub is the central block. That will contain 2 USB hub chips. And above, we have our power management systems that will supply battery charging power at high voltage, as well as power management and delivery for all of the components that will be on our development board, chips and everything. As far as the communication subsystem, I just went over it a little bit, but we have 2 hub chips, the 7252, which will provide high-speed USB outputs, 3 at 10 gigabits per second, and 1 low speed. It's called a USB high speed, but for our sake, it's the low speed USB at 480 megabits per second. We have a second chip that is only providing those low speed USB lines at 480 megabits per second. So in total, we have 8 lines out, with 3 of them at a high speed. One of the great features of this is it natively supports back compatibility. Not everything that is already in mission is going to be a new fancy USB, so it will support all the old compatible USB devices that are already up there. And it's a modular design, as I just touched on. This device will just simply be mirrored and doubled to implement in the overall laptop once that gets integrated.
I deal with the power distribution. This board will be able to handle bi-directional high power with up to 240 watts, 48 volts through power rails. It is bi-directional power flow. We're using 2 IC chips with buck regulator for step down voltage, as well as another IC chip for a buck boost to step up and step down voltage. It is designed to convert the incoming 48 volts to tightly regulate 20 volt paths. The buck boost converter will use the GIPL, enable the resistor ladder to convert 20 volts to the main rail to 5 volts, 20 volts to 48 volts depending on what is needed for the devices, as well as the desk battery support system. This will allow it to turn on with 0% battery, so if it's dead, we will be able to turn on with no battery, with no power. We're using 3 different chips for this part. A buck regulator just to use for a 5-volt standby, a switchover circuit for efficiency, as well as load drop regulators for sensitive ICs and power development negotiations to deliver the correct amount of power, the voltage and current. This ensures a safe and controlled system boot, powering from the port manager to the port controller, and the 3-level buck regulator controller first for power delivery. Up next, the extended power range power delivery management. This negotiates the power from the port controller. This figures out what device is connected to the development board. It will detect what type of application is needed, if it's a keyboard or mouse, anything more high level, as well as protection. We also use a port manager for voltage and current requests. It negotiates up to 248 volts and 240 watts. It both enables power sync for system charging as well as power source for powering devices.
Hello again, long time no talk. So the power tree is going to take 20-volt main power rail, and that will support up to 12 amps of current. We're going to step that down to 5 volts, and we're going to allow that rail to handle 8 amps of current because we need to power all the downstream devices, which should be about 7.5 amps at full usage. That 5-volt rail will also feed many of our onboard systems. We're going to step that further down to 3.3-volt bus. That'll power our USB hubs. And then we also need to set that down to 1.15 volts for the V core of our USB 7252 IC.
This is our high-level preliminary validation and testing plan. So this is to ensure that our board works as we intended. So first is the power verification. We'll verify that all the critical power lines, specifically the 3.3 volt hub supply and 5 volt V-bus, they are stable before they power the whole system. And then the USB communication testing. So that we will enumerate the board both on the upstream and downstream sides, and we'll see that the hub is detected and initialized across the whole system. For the transfer speed testing, we'll verify if the USB 2.0 and 3.2 is giving us the intended performance. Then we'll verify the signal integrity validation, and we'll use tools like eye diagram to see the quality of our signal. And if the eye is open, then that basically means that the receiver can differentiate between logical high and low. But if the eye is distorted or closed, that means there is noise and jitter, which can really affect the data transfer. Next is our board power delivery and fault protection. So we'll validate by seeing the output on the V-bus delivery output, and then the overcurrent protection and the overvolt protection response. We'll have to validate that to see if the system can turn itself off in case of fault conditions. So this is to ensure that the board gets the power, and then we can have reliable and safe data communication across all the ports.
So in closing, we're going to have schematics finished this spring. Next fall, we're going to do PCB layout, hopefully print a PCB and test it. I'd like to thank Mr. Justin Batista and Mr. Jeff Stevens for all the support in this project. Any questions?
All right, thank you, team. We're out of time, so we're going to go to the next team. So thank you.
our next team from University of Houston Clinic, Team Space Depot.
Good morning, everyone. We are Team Space Depot. Today we'll be presenting our passive capture tool dog. My name is Arib Ahmad, and I'm accompanied by my teammates Kareem Khalil, Wyatt, Ben, and Ethan Fitzpatrick. Today we'll be covering the background, project goal, criteria and constraints, decision matrix, locking mechanisms, followed by CAD model, manufacturing, physical prototype, analysis, codes and standards, references, finishing off with conclusions and opening the floor for some questions. To give you some background, extravehicular activities, or EVAs, are critical for maintaining the International Space Station. Currently, astronauts use manual toggle locks, which are secure, however very difficult to operate, especially with bulky EVA gloves and during times of high fatigue. Tool risk can also cause damage to other equipment. Our main objective was to design a passive, single-handed docking system which was ergonomic, glove-compatible, and reliable in microgravity conditions. To achieve this, we focused on 4 core principles: passive operation, human factors, reliability, and integration. This slide shows a picture of the pistol grip tool, which is the main tool used by astronauts during maintenance operations. I now pass it on to Kareem to take us through the criteria and constraints.
Thank you, Rudy. So I'm going to go over some criteria and constraints given by Micro G. So this is some performance criteria. So we want every mechanism that we use to be simple and reliable. So only push, pull, or sliding motions. We want it to be fully operable with only one hand. Proper integration with the mini workstation swing arms, and a high success rate during the repeated tool use, and ergonomically designed for the bulky EVA gloves and the suit overall. Some environmental and safety constraints is that it must operate in vacuum, microgravity, and temperature extremes. No sharp edges, loose parts, or pinch points. And to go over some of the physical constraints, our design must fit in a 5" by 5" by 5" volume, and the mass must be less than or equal to 2 pounds, and it must be able to carry a load of at least 15 pounds. And for any linear actuated forces, it has to be less than or equal to 10 pounds force, and for any rotational actuated forces, it has to be less than or equal to 1.5 inch-pounds. And the hole pattern to attach it to the tool and to the mini workstation swing arms is the 1" by 1" square bolt hole pattern. For some manufacturing constraints, any materials that we use must appear on the MBL approved material list, and for any 3D printed components, it has to be at least 75% infill, and any openings must be less than 0.5 inches or greater than 1.4 inches, and the factor of safety has to be at least 2. Here is our decision matrix. So we compared 6 different locking mechanisms to the customer requirements, and this resulted in the linear snap action and the T-handle body tint to be our top 2. So I'll go more in depth in the linear snap action mechanism. So it utilizes 2 leaf springs with a pin, and so the pin is passed through the leaf springs, and the springs are flexed in order for the pin to pass through, and then that will be locking it. And to unlock it, you just pass it in the reverse direction doing the same motion. This is going to be the first of the 2 locking mechanisms for our design. Then we have the T-handle body tint. So it's going to be a T-shaped handle attached to a shaft. So when you press the top button, the top red button on top of the handle, it's going to retract the balls inside and allow it to pass through the interface. And once you release that button, it's going to push the balls back in place, making it lock in place. This is going to be the second of the 2 locking mechanisms. And now I'll pass it off to Liet to talk about our CAD model.
All right, thank you, Kareem. So the final prototype is going to be around 3 by 2 by 3 inches, and it will consist of 2 sections. We have the bottom half, which is fixed to the astronaut's tool belt, while the upper half is detachable and is fixed to the pistol tool grip. We have a total of 6 parts that constitute the body and the locking system. We have an ABS body, PETG leaf springs. We have stainless steel parts, which consist of a T-handle body tint and a lash plate, which are screwed into the detachable portion of the system, steel pins that hold the leaf springs, and a T-handle body tent interface that is screwed into the fixed portion of the tool dock. We also have aluminum parts, which is essentially just a pin and a slash plate, and that is screwed into the detachable portion of the tool dock. Now, I'd like to go into how the locking mechanism actually works. So this video shows the pistol tool grip, and it actually shows how the pistol tool grip is attached to the body. And it also shows a cross-section view of the actual locking mechanism. Now, for the unlocking process, the red button on top of the T-handle is going to be pressed. This allows the T-handle to pass through the interface. Like that. Now, in this position, the aluminum pin is right below the leaf springs, which is what's in green. This allows for the astronaut to let go of the button and grab the pistol tool. Afterwards, the astronaut simply needs to raise the tool upwards with a certain amount of force, which allows it to clear the springs. Now for the locking process is the exact opposite. The astronaut lowers the tool into the dock, pushing down with enough force to clear the leaf springs. Like that. Then, what the astronaut needs to do is just press the button and push down, which locks the mechanism. Now, for the manufacturing, we have three 3D printed components, three ABS bodies and two heavy leaf springs. And we have machined components as well, which are then worked together. And this is what our physical prototype looks like. Figure 8 shows a cross-sectional view, and figure 9 shows the fully assembled passive catcher tool dock. Now, I'd like to pass it on to Ethan Fitzpatrick for the analysis.
Thank you, Viet. So first, I'd like to talk about the stress analysis of the housing screws that hold the lower halves of the passive capture tool dock together. So we have 8 M2 by 16 millimeter carbon steel screws, and there are 8 of them total. And we're going to be operating under a factor of safety of 5 for extra safety. And we'll be referencing Shigley's Mechanical Engineering Design book for all of the calculations that will be performed on these screws. On the bottom left is all of our material properties and givens. So for a worst case scenario, our first failure mode is thread stripping, so the nut being sheared off or taken off the screw. So the allowable force for that thread stripping is 286 pounds of force. And for the second worst case failure mode in single shear, so that's the screw actually being split in half, we get an allowable shear of 178 pounds of force. Now, taking those two worst case scenarios, we get a combined stress, an allowable combined stress of 12.4 KSI or 85 megapascals, which is less than the yield strength. Next, we'll be showing the finite element analysis of the PETG leaf springs, in which there are 2 total. So this is a very simplified setup in which we're assuming about 5 pounds of force acting on the spring by the aluminum pin. And some assumptions that are being made is that the force is acting on the entire front face of the leaf springs and that the ends are fixed, though we know that this is not the case, but it lets us know the stresses that will be acting on the spring, so it gives us a good idea of what we should be looking at. And performing a fatigue life analysis, we get really high cycles. So this part is not something that we're particularly concerned about, but because of our modular design, we can replace the leaf springs if we see that there is wear or failure in that part. Lastly, I'd like to discuss the analysis of the T-handle ball detent locking pin, which is made of 17.4 stainless steel and is 3/8 inch in diameter, and we're operating again under the same factor of safety. We're referencing the Fixture Works quick release pins and fasteners, which gives us all of the rated forces and stresses that the part can withstand. So the first failure mode is axial stress, and we get an allowable axial force of 115 pounds of force.
And for our second failure mode, double shear fracture of the actual balls, we get an allowable shear of 2,000 pounds of force. And combining these scenarios, we get a combined stress, an allowable of 3,500 PSI, which is less than the yield. For the codes and standards, just to give it very simply, this gives us our human factors and expected forces that the part will be experiencing. It also gives us our geometric constraints that we have to follow, and other design considerations about the conditions that the part must be able to withstand. Here are our references. And in conclusion, our device works, and future consideration is to see how long it will be working. Thank you. We're opening up for questions.
Questions?
So right now I see that your device is 3D printed. Is this only for testing, or is that intended for flight use as well?
So the design is mainly for considering during the NBL test, so just under the water and making sure that it actually operates in that simulation of space. So the actual materials that would be used would have to be considered by NASA if they wanted to change the material.
Okay. And part of my thought is that some of these materials they change with when you put them in water, in particular your PET. And so do you guys have plans for testing in water before you actually take it to the pool?
Yes, that is part of our future consideration, making sure that it does operate in those conditions. Again, there's more future testing with the actual physical prototype that we want to do.
Other questions?
You mentioned that you had a constraint on infill percentage, and I wondered if that was really more of a density constraint, or whether it was really a requirement, maybe about waterproof that you're speaking.
Yeah, it is an NBL constraint, so making sure that it actually sinks, and that is what the infill is for. I'm sure part of it is to the strength of the part itself.
So have you looked at the stiffness changes that you're going to get in your locking spring mechanism with extreme temperature change?
I'm sorry, can you repeat the question?
So your spring, your leaf spring that's locking in initially, right? Have you looked at how its stiffness changes with the extreme temperature changes that you can experience in an EVA?
So we were only considering for the pool, so the effects of the temperature extremes we haven't fully considered. So that would probably be another material decision that would have to be made later if they figure that the device works and we want to change it so that it is completely operable in space and withstand these conditions.
We have one more question here. No? All right. Well, thank you, team. Okay. Let's thank our second session teams again. And we'll take a very short break as we get set up for the next set, and we'll resume at 10:10.
We're about to get started again. All right, welcome back to the next session. Our first team up is from UT Tyler, and they are Team Ether.
Good morning, everybody. We're Team Ether. I'm Alex. I'm joined by my teammates Abbott, Eddie, Steven, and Brandon. We're all mechanical engineers from the University of Texas at Tyler, and our project is the designing and manufacturing of the lunar Martian surface habitat module. So for some general background, at this point we're all familiar with programs like Artemis and NASA's plans to establish human presence on the moon and beyond. Our project fits into NASA's broader Moon to Mars architecture by addressing the need for reliable, long-term habitat units. We also considered manufacturability and launch constraints, designing a concept that can be built on Earth using existing aerospace fabrication methods and launched with realistic payload limits. Our general concept statement, our idea was to design an extraterrestrial habitat module suitable for lunar and Martian missions, which can be fully manufactured and prefabricated on Earth, such that it can be launched pressurized and configured ready for immediate deployment upon arriving on site. And here's a view of our final design, the Aether module. As you can see from its cylindrical shape, it's inspired by proven vessels such as propane tanks and high-altitude aircrafts, which are highly effective under external pressures. The module is designed to stow and ship fully configured, helping to reduce potential risks faced by crew members by eliminating the need for complex on-site assembly. And most importantly, it's designed to be compatible with both lunar and Martian conditions, making it a flexible solution for future exploration.
Here we'll talk about some of the internal layout of the Aether module. As you can see, there's a raised loft which helps maximize the usable floor area, while the pressure vessel allows for normal cabin pressures, and the structure is also supported. The structure is also supported by an internal support spine over there, as well as external saddles. And over here you can see a little bit of our testing for our meteoroid testing. And in ANSYS, as you can see here, we simulated the worst case possible scenario of a millimeter diameter projectile traveling at 20,000 meters per second. And as you can see, the projectile was successfully stopped with only 10% penetration into the shield. And to the left, you can kind of see a little bit about how the layers are set up.
Hello everyone, my name is Eddie Hidalgo, and I will be presenting the thermal performance of the habitat along with the brief overview of the ionizing radiation shielding. So here for the thermal performance, for this analysis, a constant interior temperature was prescribed to to represent habitable conditions within the habitat. External temperatures. All right. Okay, we're just gonna go on this one. Okay. So quick before it changes again. So we were able to meet the specs of maintaining an interior temperature of range between 18 degrees Celsius and 27 degrees Celsius. All right, next slide. So this is our ionizing radiation shielding. So our specs was to have an amount of aerial density of 10 grams per centimeter squared. As you can see in the loft area, we exceeded that requirement of having 16.32 grams per centimeter squared. And for the non-loft area, it was 7.63 centimeters squared. And so we were able to meet the spec for the loft area. However, the non-loft area we weren't, but this reflects the deliberate design trade-off. Rather than applying high-density shielding to the entire structure, the design prioritizes critical regions and reducing overall system mass. This highlights a key engineering principle balancing performance, mass efficiency, and while maintaining feasibility for deployment and transport.
Okay,
going to talk to you about the coupled analysis. So basically, part of our requirements was we had to make sure this module could withstand a mission of 15 years. But we're talking about harsh environments like on the moon, on Mars. Like for example, on the moon, they'll be experiencing temperatures on the dark side for like negative 270 degrees Celsius. And that's going to be for like 14 and a half days. Then we rotate, we're facing the sun. We have temperatures of 121 degrees Celsius, just the solar flux just beating down our poor little module. So we take our thermal analysis, we apply a thermal load, and we transfer it to a structural analysis. We apply pressure and gravity. We get those stress values and plug them into a series of equations. We get the Goodman correction value. This is the stress that our module is going to experience within that thermal cycle. Over 15 years, the moon will undergo 185 cycles, and Mars will experience 5,475 cycles. So we look up the SN curve for aluminum 2219, which is the material for our pressure vessel, and we use the Goodman value to find the number of cycles to failure. We then find the safety factor by dividing the number of cycles applied by the safety factor cycles, and we're able to meet those the NASA standard of a safety factor of 2 or above. After 15 years, Mars will have a safety factor of 2.41, and for the lunar environment, we'll have a safety factor of 2.24.
And our final portion of analysis is the vibrational analysis during the launch conditions. No point in designing all of this if it can't survive the rocket. As you can see by the graph here, our margins of safety for buckling analysis during launch, it's worse structural environment. It is more than well and robust enough to help the support spines to survive launch. In fact, it is more likely for a total system collapse than any imperfection or manufacturing impurity to ever ruin the strength of the structure. And all of this was validated against David Bushnell's Panda 2 methodology. If any of you NASA guys in the audience know what that is, appreciate it. And then finally, for the FEA analysis of our design, we have a maximum deflection of around 1 meter, which is based on the max. So that's well under the maximum for regular construction regulations, which is length divided by 200. So at a 10-meter length, this is overall negligible. It's practically flat, perfect 180 degrees parallel, and well under the length divided by 200 requirement that most construction standards have.
So just to wrap up, in conclusion, our module meets all of our design goals through a prefabricated rigid habitat optimized for the conditions on both the moon and the Mars. We achieved a balance between manufacturability, environmental resilience, and mission sustainability. And we believe that it provides a scalable foundation for future service systems aligned with Artemis and Mars mission standards moving forward. First of acknowledgements, we'd like to thank TSGC, our NASA mentor, Robert Knuckles, and our faculty advisor, Dr. Mohammed Biswas. And thank you.
Any questions?
So regarding your FEA analysis of the cylinder, when it comes to doing a buckling or a collapse analysis of a pressurized vessel, the end caps, because there's a, as you mentioned with the geometry, it's no longer just round at the ends, there's a discontinuity, and that imparts a lot of stress on the structure. So did you guys also account for the end caps, or did you guys just do the cylinder itself, like in the figure?
We did account for the end caps. We added the bonus mass for stress concentration for as worst case scenario. Basically, the load on the structure was, I'd say, around at the maximum of 10,000 kilograms, and that is the maximum deflection that it gave us. So worst case scenario, max weight, only 1 millimeter.
Other questions?
What assumptions did you make related to pressurization of the habitat for ingress egress cycles?
Our assumption of pressurization is that it is pressurized once on the surface and connecting to a series of modules as a modular base rather than a single independent component. So we made the assumption that it would be pressurized once and ideally never depressurized at all.
Other questions?
How does it go from lander to location where you want it on the moon?
That's not in scope.
To be a little more specific, we do rely on some assumptions that it will be part of the larger on-site infrastructure. It wouldn't be a standalone unit, so things like a sky crane could be used to assist in deployment of the module once it's on site.
Kind of a follow-up, pros and cons or the rationale, I mean, launching pressurized versus unpressurized, it seems like, I don't know, it just doesn't feel right, launching pressurized is the way to go. Can you explain the rationale?
If we were to launch in pieces and construct it on sites, if I remember correctly from our mentor Knuckles, bringing the air to repressurize it if it was an inflatable or anything like that would be a separate rocket on its own. So we decided that building it on site and pressurizing it here is the most effective solution rather than a second trip.
Any other questions? All right, thank you, team. All right, our next team is Texas A&M 12th Man Biofrontier.
Howdy, everyone. Howdy. All right, so as you know, we are 12th Man Biofrontier, and we will be presenting our second semester work on the Astro Ring. So, meet the team. My name is Austin, this is Ricardo, this is Rashik, and this is Carson. We'd also like to take a moment to thank both our mentors, our NASA mentor Philip Augustine and our faculty advisor Zachary Bunot. And if you'd like, you guys can contact us at the email below. So to start off with our problem statement, as we all know, currently astronauts suffer from muscle atrophy in space. The small environment of the Artemis craft limits options for muscle atrophy countermeasures. So we were tasked with developing some type of supplementary countermeasure that's compliant with size, power, and weight in order to maintain astronauts' strength during these long duration missions.
A little bit of a background. On the Earth, you have your natural muscle or bone loading just by gravity, by walking around, by using exercise equipment. It's a lot of variety and a lot of different things you can do to counteract that. In space, it's a little bit more of an issue. So on the ISS, they have several devices such as the ARED, the T2 treadmill, and the Cebus cycler, which are all shown in those images below. We were lucky enough to be able to tour that location and to see it. These devices are massive. They're very effective, but they are huge, and it's only huger in person. That's an issue for Artemis spacecraft, where space is an extreme premium. So they've developed a flywheel that's compact and lightweight, developed specifically for Artemis-style craft. It provides that resistive and cardio exercise, and it's effective, but there's less variety than an ARED. You're basically only limited to rowing and squats. And if you're exercising for 2 hours a day, like astronauts have to do, over months at a time, potentially, with these Artemis craft, that can get a little boring. How do we solve this? So the question we asked was, how can we keep long-term exercising engaging and effective within the extremely confined space of an Artemis mission?
So let's talk about user needs. After speaking with 6 different human spaceflight experts and even having first-hand conversations with real astronauts through our human health and space class, we were able to determine that we needed to mitigate muscle atrophy while also maintaining our device compact and small. Most importantly though, we needed to have it be fun and engaging for the astronauts. In order to comply with user needs though, we needed to make sure that the device was safe to use, that it performed efficiently, and maintained its engagement over long periods of time, was easy to use, learn, and handle, and was cost efficient to produce.
So what's the deal with the Pilates ring? The ring provides a portable way to utilize multiple muscle groups through gravity-free resistant exercise. But why stop at just exercises? Movements can be performed during the exercise that can be used as inputs to perform actions in a game. These inputs then provide audio and visual cues and feedback, which is all housed within the ring. A repetitive routine workout is now a fun pastime you want to keep coming back to. Current literature supports supplementary exercise use to increase pec, tri, delt, lat, and rhomboid endurance, supports abdominal and obliques, and hip adductors and abductors, glutes, as well as the pelvic floor muscles.
So let's talk about some design specifications. The ring is really small, coming in at only 14 inches of diameter, and is very light, at less than 2.5 kilograms in weight. It offers a fiberglass core, which offers a resistance of 2 pounds of force per inch of compression. It features a Velcro safety system and has RGB LED integration.
As for software, we wanted everything to be housed within this handle alone, and so we used a small microcontroller. It's a Raspberry Pi-based thing on an Adafruit RP2040. You can buy it for $20 off of Adafruit. It's got an accelerometer and a thin film pressure sensor to detect reps, and it has a speaker, LED button, and LED strip for the UI.
To start off, safety is a high priority. The concept is to use a sheath to minimize debris risk. It's a double-layered sheath, with the first layer being a polyester reinforced EDPD rubber for strength, and the inner layers are smooth plastic so it's easy to clean and reusable. This can be done since the sheath is attached via Velcro. The sheath layers over itself to fit the ring's curve while ensuring a gapless coverage.
We conducted 5 partial compression tests and 1 maximum compression test to characterize the mechanical capabilities of the structural integrity of the Astro Ring. Some key outcomes from these experiments were that the Astro Ring provided an average resistance of about 2.16 pounds of force per inch of compression, which means that the exercises can be as intense as the user wants them to be. The Astro Ring also withstood a maximum stress of 132.37 megapascals without any observed deformations or failures.
As for the hardware, here's a picture of the inside of the controller, which we have here. As for the software, we have a Circuit Python-based software, which we're able to make multiple self-contained games, like Bop It, or a rep counter, or things like Hot Potato, which the astronauts can use amongst each other. And there's also computer game integration, which we'll show later. This met all of our user needs for the hardware and software, meaning that it needs to be comfortable and lightweight, and also engaging and effective. Since a lot of this project is human factors based, I did a lot of UI testing according to ANSI and HE75, human factors engineering, and I applied the comparison test for early design phases. We had 4 separate iterations of the UI, and I interviewed a bunch of my people, steadily improving the UI over time.
So as for the data acquisition, if you guys noticed last semester, you might know we wanted to include a PPG IR sensor into the kit. Unfortunately, we weren't able to do this due to unable to produce a reliable heart rate signal aligned with IEEE 1708 during our testing. Basically what happened, roughly 40% of our signal that we detected was noise. We couldn't accurately distinguish between heartbeats and just a regular Pilates ring movement, so we had to pivot. So we chose impulse. Why impulse? Basically, it can capture both effort, magnitude, and duration, and it can be computed with our existing hardware within the device. It relates exertion to force or resistive exercise, force and time, and rewards the user for holding the squeeze longer.
Our prototype has gone through various iterations, starting as an exercise ring with a battery and an LED array taped to it. The ring now features a speaker, LED button, sheathing, and software to utilize all the above. The sheath itself is now integrated into the ring and can block heat from LEDs reaching the user via an integrated reflective plastic on the inside. It acts as a last line of defense in case of a ring fracture, while allowing the LEDs to be visible through a window. The handle has gone through various material changes to allow its footprint, or to decrease its footprint, while increasing the strength and modularity through its current three-piece design, isolating the electrical components into a section sandwiched between the two handles.
As for the software iteration, we created custom code for the players. We have currently on Red Player, there are 4 players for each of the Artemis astronauts. We created several games, player handling, settings, rep detection, etc. We also integrated it with a computer and sampled for the UI and design phases. So after this, let's do a little demo. This is a game that we made that's integrated with the computer. Not only is it just for our proprietary games, but you can also use it with other games like the Dinosaur game. This basically maps keystrokes to our inputs, and it can be used in tons and tons of different applications. We're excited.
So, some future design considerations. Obviously, we would love to reintegrate a PPG/IR heartbeat monitor into the device in order to track data logging for mission duration crew. Also, we want to integrate with the crew health monitoring systems within the Artemis. And structural safety, we'd love to switch out the material to a steel core in order to provide a more resistive exercise, and also develop multiple rings with variable compressive resistance in order to increase the versatility within our device. So, in conclusion, this device is to be used in conjunction with the flywheel in order to mitigate muscle loss during long-term Artemis missions. It's going to provide resistive or cardio exercise with gamification for the motivation of astronauts. And it's going to promote competition and team building within the crew using player-specific stats and games. Also, the safety features and the lightweight design ensures effectiveness and engagement. Thank you guys, and we'll take any questions.
How did I know a question was coming from this table?
Could you tell us more about the power supply in the device?
Yeah. So there are 2 ways to power this device. One, it's completely battery only. So there's several games like the Bob Bed or the Rep Counter. You can use it just with the battery, and that's a 3.7 volt, 2200 milliamp power supply. And that battery is also charged by USB-C onto computers. So you can just plug it into any computer that the astronauts have and use those games and use that charger.
Other questions?
If it is dropped or thrown by accident, can the electronics survive the impact?
Yes, we haven't done vibration testing quite yet, but all of the electronics are here. Not only are they directly soldered to the board, but it's also, the handles are removable, so astronauts, if something happens to break, they can just go right in here and fix it themselves.
So for the device, you say cardio and resistance exercise training. So I kind of have 2 questions in one. One, what is the plan or your goal? What would be the exercise prescription for it, for using a Pilates ring? Especially cardio-based, how long would you have to use this ring? You know, sitting there, squeezing it, whatever part of your body, upper body, lower body. Realistically, is it going to give you that cardiovascular training? And then with that, what is the goal or purpose with the heart rate monitors?
be a supplementary device with the flywheel. We want the astronauts to be like engaged in using the device. With the PPG heart rate sensor, we wanted to be able to basically record our heartbeat and then send it back to NASA in order to basically track the astronauts' use for it.
In addition, with actual conversations that we've had with astronauts, we found that they sometimes neglect medical or exercise devices just because they find them boring. So this is meant for, to stimulate exercise even when they don't want to have them have fun, and to have them basically trick them into having exercise, basically.
Have you guys considered anything with grip strength?
Not traditionally. Those would be, you can get those grip strength things, and it can be carried up with the astronauts themselves if they want to do that.
Well, my point is, it would give you a larger variety of games to play as well. Grip strength is really important for when they're doing EVAs. Crews really need that.
We could integrate the, there's a little grip strength thing on the handle. That'd be cool. That's a good idea. And also force sensors within the handle, so if we wanted to make a game like how hard we can press, we could do that as well.
All right, one more question?
I know we talked to y'all yesterday. I was curious if y'all did any testing on the muscles to record like data to actually prove that this does help muscle atrophy. I don't know if you like looked at literature. I also want to kind of go back on what Kayla said. What is the exercise prescription for this? How long are you recommending it? What intensity? Is it kind of what's comfortable? Like, I'm really curious about that.
So for the muscle groups, we looked at current literature. When Ricardo was demonstrating the pec tridelt, abdominal oblique, and the glutes, as well as the pelvic floor, those were all from literature. We also looked into like rehabilitation and utilizing the ring as a device to supplement that.
That was one thing that we got when we were talking with the astronauts that came to our classes. They were saying astronauts frequently get injured, actually more than you would expect, and so this would not only be used for as a supplementary to the more like intensive flywheel exercise, but also for rehabilitation with the astronauts.
And what's the prescription?
Prescription, yes. That would be after we get the data from like the Fitbit that they have on the Artemis tracker. Then we could use that to inform more of our prescription. I don't want to. We want to get the data first before like sending requirements to the astronauts.
Right, and based on like the literature you said that you read of the muscle groups, is there an intensity like that you suggest just in general, or like a time duration? Because I know you said that they have that 2 hours that they're recommending to exercise, and this is a supplement tool to use. So are they doing like, this amount of time with this, and then going in and doing the Pilates ring for this amount of time? Like, do you have a recommended time that you see benefits from using this ring, or is it kind of like they do their 2 hours and then after they kind of use it as like almost like a fun like activity rehabilitation, like just to kind of work on those muscle groups that you said, like?
Yeah. Your latter statement would be the goal for this exercise. Again, like if we were to get a prescription, we would compare the sensor data from this with the sensor data from the flywheel, and then see like what are the times, what are the similar heart rate or exercise amounts in there, and then go from there.
All right, thank you, 12th ladies.
Our next team is from Texas State, and they are Password Bobcat.
Hello, we're Password Bobcat, representing the hazard detection module for the integrated camera and lighting system, or more broadly for lunar terrain vehicles. The goal of this project is to optimize the visual quality of the head of the vehicle, and our method of doing this is using millimeter wave radar, which is unaffected by lighting and regular interference. And so with this radar, we can detect hazards and essentially present the hazards as bounding boxes to the operator, as well as to downstream systems, where these are like the safety systems, and we're doing the initial sort of data collection for the automation. So the main takeaway from this presentation is not only how we're doing this, but also how an operator could configure our system in order to optimize it for their specific scenario or their specific vehicle.
I had the digital signal processing subsystem that was working with the radar board, our development board directly, to create point cloud data. It starts with the transmitter antennas. It sends out a chirp signal, and it gets reflected off of the surrounding objects, received by the receiver, and processed into point cloud data. That looks like X, Y, and Z coordinates that represent the location of the object relative to the radar board. It also includes velocity and the signal-to-noise ratio. All of this gets computed from the signal components of that received reflected wave. We configure the radar board by placing a configuration file on our Raspberry Pi CPU. It sends those configuration settings over to configure both the radar front end, control things like range resolution, correlated to the chirp rate and the chirp duration, and it also applies settings to the digital signal processing to affect settings like CFAR or constant false alarm rate. So whenever you look at the output of our system, you'll notice a couple of things. You'll see a cluster of points that represent the object seen by the radar, and then you'll see a cluster of points near the origin, and that's going to be right in front of the radar. And you might be thinking, where's the rest of the environment? Well, CFAR, that constant false alarm rate, filters out points that have a weak signal reflection. So that is why you see right in front of the radar, where signal strength is the strongest, a cluster of points, because it passes that CFAR filtering process. And the user can configure that CFAR setting so that they can reduce the noise that is shown from the environment. But as long as that CFAR setting is set to or below 35 decibels, you will get that ground cluster. This ground cluster is important because it serves as a baseline for differentiating positive from negative hazards. Positive hazards being rocks and negative hazards being craters. We performed a couple of tests on the radar, two of those being the most extreme cases that we promised to be able to detect that last semester, 30-meter range and 4-centimeter range resolution. So basically, the distance that two objects can be differentiated from, the distance apart that they can be differentiated from as two separate objects rather than one object. And we proved the ability for the radar to be configured and successfully detect under those two conditions within 2.5% error. The caveat to this is as you increase in range, you decrease in range resolution abilities. This is due to the limited bandwidth of the radar. However, it just reinforces the fact that the user can configure our system for whatever situation they're trying to detect.
Next, we're going to take this data and we're going to need to move it over to the Raspberry Pi. And I'm going to be reformatting this into an open 3D point cloud and then depositing it into a LightFlow buffer for spatial intelligence to take the frame and process it. We're using a LightFlow buffer because we were emphasizing freshness over just completeness, and so we don't want to have to work through stale frames. We just want to get the spatial intelligence, the most up-to-date data. And that's for latency, which we can show. I have these hardware tests which show that our latency is still very low, which shows the scalability, speaks to the scalability of this subsystem and the connection between the two subsystems, the DSP and the spatial intelligence subsystems.
So what is the spatial intelligence pipeline? This is where we are taking the optimized point cloud data, now that it's converted into this Open3D, which is a library that's optimized for computer vision. We take it and we can now process it so that we can actually start making sense of what are these points and where are these hazards. The first step in doing this is clustering. So we take a point, all the points, and cluster them with their nearest neighbors. You have to remember that only the detected anomalies show up as points in the scene. So every point that we see in our scene is either belonging to a hazard or it's a noise point. It's kind of left over from the CFAR filtering. So the parameter that's being swept on the screen is the clustering radius. This is something that we can increase if we're trying to increase the resolution. In this scenario, you know, a hazard is only one. There's two 1 meter hazards, but maybe our threshold for the LTV is 2 meters, so we can increase the resolution. And downstream, this reduces the processing. And then the second parameter for this that the operator can dynamically manipulate is the minimum point count. And this is another filtering stage where, because we know that points are evenly distributed across a hazard, then bigger hazards will have more points. So we can increase this value to only show the large hazards, depending on the environment and the vehicle. The next step is baseline calibration. So this is where that ground cluster comes into play. We can take the average z-value of this ground cluster in order to create the baseline. And for our system, the baseline is the plane that's tangent to the bottom of the wheels of the limb terrain vehicle. So from this baseline, we can now classify the hazards as rocks or craters. And this is important because driving a vehicle and lighting the scene, you would do it differently with an above ground hazard versus a below ground hazard. So this is a full system test. There's a lot going on here, but the main takeaway that applies to what I just described is that uncalibrated frames are actually more computationally expensive than calibrated frames. And it seems counterintuitive because we do more processing with calibrated frames, but this is because the bulk of the processing is carried by the clustering module. So if we're not calibrated, then we're including the ground cluster as part of that module, and so we're having to do more processing out of it. So always better to calibrate the system unless you absolutely don't want to. Tracking and smoothing, this is the last step that I need to cover, where we have our bounding boxes, but there's no continuity. And the way that we can fix this is by applying tracking, where as long as the bounding box is within a threshold intersection over union of the existing track, then we can add it to that track. And if it disappears and then reappears in the next frame, if it's too far away to reliably detect, we can still track the bounding box as it's moving, because it carries over for a couple frames. And those are two parameters that the operator could adjust depending on the range that they're trying to detect and the velocity of the vehicle. And then smoothing is more for visual continuity of the movement. You would want to favor the tracked bounding box if you're really looking at the bounding boxes, but otherwise better to favor the current bounding box if you want a more dynamic response. So for the spatial intelligence subsystem on the Raspberry Pi, it's very scalable. We only look at around 50 points currently, and that this is kind of a worst case value. We're looking at 1 millisecond, and then it just increases about 20% as fast as the point density. So if we could get more points into this pipeline, wouldn't be an issue. Actually, most of our processing is eaten up by the interface and the rendering for the development stage.
All right, so like Mason just mentioned, once all this data gets collected and classified, it needs to mean something to the operator. So I was in charge of figuring out how the operator is going to interact with our system and how it's going to visualize it. So what we've got right now is a small little touch screens. We chose that just because, for prototypability and cost, it's just really easy. It's a little Raspberry Pi. And what that does for us is it provides a little mini map of what the radar is seeing in front of it, and it puts those bounding boxes on it. And like Mason said, the real latency is coming from the rendering of the interface. So you can see on this graph on the left, at 1,000 points and 50 bounding boxes, it only takes it 208 milliseconds to render, and average human reaction time is looking like 250 milliseconds. So it's a near constant stream of your hazards. And so once we figured out how we're actually going to provide the information to the operator, we had to figure out where we're going to put it, how we're going to mount it. So the trick here was we don't have the exact specs for the LTV or whatever vehicle they want to put it on, so it needs to be an adaptable mount rather than a fixed mount. And so you can see on the left, we've got little links that attach to the frame, and then those attach with like a little squat rack mount to the previous team's structure. So what this allows us to do is you can just add or subtract links to whatever your mounting structure is. And you also see the modularity. We have it mounted on a tripod. That's primarily for testing, and the lab situations are showcased like this. And so now that we've got all of our subsystems talking, looking forward into the future, we'd like to get the radar and the lights working in conjunction. One idea we had for that would be, as the hazard is approaching, the radar would tell the lights to dim as you approach to avoid washing them out. So that's just one idea, looking forward into the future for this project. And we'd like to take a second to thank our TSGC sponsor, our faculty advisor, and amazing people here who put this on every year.
Thank you.
Questions?
How does your latency compare to industry standards for self-driving cars?
Currently, it's a lot greater. It's because of the way that we're rendering it. It's greater. Where we're at with the self-driving cars, they're not having to render their data. So, as far if we cut off before rendering, then we're right on target. And then once we get above that, it's about 250 milliseconds, which is still human reaction time, so we're only doubling reaction time, which isn't a problem for slow-moving vehicles. But really, this is an automation system for safety of the vehicle, and so it is an important factor, definitely.
And I was wondering also, the ops concept for the lunar terrain vehicle is 90% uncrewed, so it has to be self-driving, and then just the 1 month a year when the crew is actually on the lunar surface. So what considerations did you make in your design for a single system being used both in the crewed and uncrewed scenarios of the LTV?
Yeah, so we wouldn't want to use this for navigation because it's only detecting hazards. So it's only for other safety systems that would apply when the hazard is detected. An example is the lighting system. The other one is just like a kill switch, like you have to stop here because there's a hazard immediately. And it would automate the system whether or not it's a crewed system. Thank you.
Other questions?
Thank you. You mentioned a couple of times about your classification. How rigorous your classification from what are the false positives that radar may identify the hazards that are really not there because of the error rates. Some of the radars have higher, at least in terrestrial applications. Also, how do you detect whether it's a hazard that is correctly identified, or is it really something that radar is seeing that is a false image or false echo of something?
Yeah. So it sounds like you're asking, like, how would you deal with like a false positive? And was that your first question?
That's one of them.
Yeah, so our radar and with the interface, you can actually tweak it to your environment. So like when we got here yesterday, we had to spend some time, because usually when we test this, it's in an empty hallway, right? And now we're in a crowded conference room. So we, like you're saying, you can see like there were some false positives, and we spent time tweaking the parameters, like Mason mentioned, so that you like tune it for the environment. Does that make sense? And what was the other question?
How accurate would be your classification for the system to be responding?
So, as far as classification between positive and negative hazards, we're calling them rocks and craters, but anything above or below the baseline, that is completely accurate because we are calibrating the baseline with the ground cluster, and so that's kind of something that we get to make it completely accurate. And then with the false positives, there will always be some noise. We have 2 layers of noise filtering. That's what CFAR that she was explaining is the first kind. And so that we have one that you can, CFAR you initialize the system with, and then we have our dynamic tuning depending on the environment. Does that answer your question?
Thank you.
Okay, thank you.
All right, thank you, team.
Okay, welcome back, everyone. We're going to start our fourth session this morning. And the first team up is from University of Clear Lake, and they are the Gamma Rays.
Hello, we are Team Gamma Rays. I'm Allison Milanovich. I'm joined by my teammates John Almilo III, Avery Barrera, Frank Blanchard, Brian Leon-Strada, and Frank Taylor. And today we are going to be discussing the development of our lunar scavenging and recycling unit, a concept we have been calling the Moon Belt. To give a brief overview of all the topics we will be going over, I will be starting with the project introduction. We will then be moving on into the codes and standards. Following that will be a recap of our previous project progression, as well as going over our concept generation methods, our wheel design, the modeling and analysis that we've done, as well as finishing up with our project planning and our future works. So to introduce our project, we are part of the Texas Spacefaring Consortium Design Challenge with topic number 109, Lunar Surface Recycling, Scavenging, and Reuse of Discarded Mission Hardware. With this project, we decided that we wanted to attack the Apollo J mission, specifically using those rovers as our payloads. We believe that this can reduce future mission costs, as well as supporting independent long-term lunar surface missions, as well as improving overall sustainability and maintainability of all NASA missions. Given our literary review, we believe that our moonboat should be weighing around 1,000 to 1,500 pounds, as well as encountering an angle of slope no more than 25 degrees, possibly 30 degrees. We don't expect our rover to engage with any craters. We also do not expect our rover to sink below 6 inches. Finally, we will only be operating in the daytime, and for our project specifically, we are only going to be focusing on the movement and lifting mechanisms. I will now be passing it over to Grant to talk about the codes and standards.
Thank you, Allison. So the first 3 codes will apply to our prototype and our model, and the last 3 will only apply to our model. The first code will be on how we design our structure and how we do our safety of factors. The second one will be toward our motors, and the third is how we'll do our electronics. So we as a group decided we are going to target the Apollo J missions. The United States has sent up around 250,000 pounds of materials total. The Apollo missions account for 220,000 pounds of that, and the J missions are 65% of that 220,000 pounds. We decided to tackle the J missions because NASA has well-documented areas of these, great images, and they have a diverse stockpile. So each Apollo J mission has 1 rover. They weigh around 462 pounds, and they are 85% metal. Now we'll pass it over to Avery to continue the background.
Thank you, Brent. So, given the fact that we're expecting to have our prototype pretty massive, we decided to actually introduce the pi theorem. The pi theorem actually helps us get an idea of how we can simulate on Earth while also being a scaled-down version. And if you may recall our recap, our expected model is actually to be 1/3 in scaling. And then when it comes to actually considering our lunar sites that we want to hit, we have to think about an optimal distance. We wanted to make sure we're efficient whenever we actually consider this mission. So then we introduced triangulation. Given the fact that we have well-documented coordinates, we're able to get an idea of the distance of these missions, and then account for our center point and how long it'll take to actually get to these distances. And in doing so, we're actually able to benchmark the Viper rover and consider its power as well as its average speed and max speed. And we developed an envelope that can actually take into account the nominal to the worst case scenario of what can be expected, given the fact that the terrain is pretty rough. And with that being said, we did calculate for a expected average speed to be about 0.25 miles per hour up to 2 miles per hour. And then we can also get a mission duration of about between 123 to 221 of operating days needed to actually have a successful mission. And with that being said, I'll go ahead and pass it on to John, who will discuss our competitors.
Thank you, Avery. So here's a list, or some few images of our actual competitors that we used when we were developing our concepts. I'd like to draw your attentions to figure 4 and 5. This is a rover where we try to gather some information on their wheels and apply that same type of technology to ours. Figures 6 and 7 are the current Mars rovers being used. And 2 things I want to draw the attention to is in figure 7, you'll see a gentleman standing next to that rover. That kind of gives you a size reference, and it kind of emphasizes what Avery just said, that our rover is going to be pretty massive, right? We have to carry something this big. And then another thing I'd like to point out is the RBS system, the rocker bogey system that they use, which we also also implemented into our current design. But now I'm going to show you last semester's design and explain why we decided to change it. So we had a track system that was implementing a tilt bed configuration. We were thinking about towing things, right? Well, there was two main issues with that. One, lack of redundancy. We had two motors. So if one motor went out, we just go in circles, and then next thing you know, we'd be another piece of material that needs to be picked up. The second thing would be dust mitigation. That track system had a very serious issue about mitigating dust, so how long before it would be able to work. So we went back to the drawing board. We went to one of our original concepts where you can kind of see here, it implements kind of a dolly system. We call this one the dolly part. And we started to expand on that. We implemented that RVS that you see right here, but you could also see the dolly part right here and expand on it a little bit more there. Now, this next image you're going to see, we decided to change the material from PVC to more of something a little bit more rigid. We decided for us to be able to manufacture this easily, that we would use an aluminum unistrut, which then led us to our final design that you see here. Now, two things that we were trying to stress. One, something that was proven, and that's going to be the RVS system that you see. And then our 6 motors. We have 6 individual motors on every single wheel versus the 2 we had on the previous. This next slide is going to show you a simulation of our model and how the bogey system will be able to swivel. That's what's going to help it traverse over obstacles. And then the next part of the simulation you'll see is our linear actuators that we're going to use to help secure our payloads. For this purpose on the Earth prototype, we're just lowering straight vertical to go down, secure our payload and lift up while keeping the payload a low center of gravity. And with that, I'm going to pass it on to Brian to discuss our wheels.
Thank you, John. Following our current design, however, we'll be building a 1/3 scale design. To do that, we had to create as well a current design for our wheels. Initially, we created this wheel, however, we did find issues after 3D printing using ABS and veggie, where we find out that our better option we had to do is print separately each part of the wheels as well, modified since the rims thickness were too small, it will cause a failure. And this is some examples about our wheels being 3D printed. Following this, we come up with our new current design where we increase the spokes of the rims thickness as well as the thickness of the tire, where this is the front view of the wheel, and this shows how the wheels will be connected to the motor. As I mentioned, we'll be 3D printing our wheels where the tire will be printed with TPU and the rim's going to be printed with PLA tough. As well, we'll be using the gyro infill. Yeah, we did a study over a percent density of 40 to 60% and 100%, where we did a compression test and we found out that 40% was the best option for us when 4 walls could use. And this is an example of our G code for our wheels. And now I'm going to pass it to Frank, who's going to talk about the electric components.
Thank you, Brian. So, after consulting the most recent literature on NASA's rover navigation in EVA vehicles and other research institutions and drawing on their inspirations, we designed a rover system that will travel to the payload and deliver it. It uses a gantry-style retrieval system controlled using educational-grade programmable controllers and actuators. It uses pulse width modulation to control the motors and linear actuators, which can be used to later integrate into a fully or semi-autonomous system. Our model assembly is planned to use the following current and power specifications predicted from analysis methods using source MATLAB tools, the basic electrical analysis, and measured current and power ratings from preliminary bench testing. This slide shows the current specifications to make sure we're not under or overcurrenting our system. And this is a power budget analysis to make sure that we have plenty of power to model, enough power to translate to our full prototype assembly size. And this is a torque margin compliance test to make sure we're within specifications of NASA's standards and codes to make sure we have plenty of torque to turn our wheels on our model and on our prototype assembly. A complete integration plan includes using visual odometry and bearing orientation for lunar travel, including cameras and a Debian-based operating system for future works. But I'll leave the future works up to Allison to finish this up.
Thanks, Greg. I will now be going over our project planning. As you can see, our project has been split up into 5 phases, with the first 3 phases being completed. We are now currently in the FEA and testing phase. This is when we simulate stresses or currents on our circuit, and we are supposed to verify them with the actual setup that we have. Unfortunately, you'll notice that it is only 50% complete because at this moment, our circuit is not done. However, we are making headway to completing that and should be completing that by our April 20th deadline. Finally, finalization and documentation. This is when we're going to wrap up all of our research and print out our final report, as well as make our final presentation. Moving forward for our future works, like I said, we are hoping to test the functionality of our rover and the lifting mechanism all by April 20th. These rely heavily on the circuit, which is why we only had a 50% completion rate at that. However, afterwards, we should be able to finalize our report and presentation by April 24th, completing our entire project. Here are a couple of our references. We thank you so much for your time and attention, and we now open the floor for questions.
Thank you, great job. My question is, maybe I missed it, what is your target maximum load that this rover can carry, both in terms of mass and in terms of volume?
Great question. So we are aiming to actually get the Apollo rover to 15, 16, 17. So scaling that down would be about 17 pounds. We're expected for our 1/3 model. As far as dimensions go, we kind of were just a bit in line with just taking on that mass firsthand and then considering the dimensions later. Unfortunately, we just haven't got to that milestone quite yet. It's a great question. Thank you for your question.
Thank you. What kind of an environmental analysis you did in which your rover is going to operate? You mentioned about the wheel structures and strength and all the characteristics, the material characteristics you considered. How much effort did you spend on doing environmental analysis in the environment in which the rover is going to perform operations? It would be good to amplify that. Thank you.
Yeah, thank you for your question. So when it comes to testing, so far what we did for our road analysis is compression tests. We haven't tried so much to get to the environmental testing quite yet. However, we did have plans to actually use like concrete mix to simulate a lunar environment with the rigorous, and then add some kind of inclines to help also get to the degrees, and also at some point with the temperature. But we just haven't been able to achieve that milestone quite yet, unfortunately.
Other questions?
So as I'm a little bit lost in terms of how were you planning to pick up the rover itself? I saw that you had 2 things on either side, but I didn't see how they were moving to be able to grasp and pick them up.
Right, so great question. For our Earth prototype, it's just, right now, just linear actuators that are going lower. The actual model that we're picking up has a nice flat bed. That's why we implemented the actual angle irons that you see on there. So it will lower down, will then go over top the model that we're going to pick up and then lift. We perfectly designed this to be right underneath that flat bed of the model that we're going to pick up. Now, when it comes to the actual model that we would use on the lunar surface, if we had the budgeting and everything, we would have it to where it could open up and come down and secure. But for right now, it's just straight down with limited time and budgeting. So try to keep it simple at first.
And I guess I thought I was looking for some way for it to go around the wheels.
For sure.
And
Yeah.
for sure come in.
For sure.
Okay.
Yeah, we would also use hooks or something along those lines because it'd just be a lot more secure to connect to the payload as well.
Yeah. Yeah, that's an excellent question. Yeah, to build on that too, yeah, we would like for the frame to actually be able to move, to kind of squeeze it in and out. But yeah, we just want to keep it as simple as our first phase here.
All right, thank you, Gamma Rays. All right, our next team is from Texas A&M Kingsville, and they are Javelina X.
Hello everyone, we are doing the lunar and surface habitat module manufacturing. So as he mentioned that we are Javelina X. My name is Alyssa Flores, I'm team lead.
My name is Garrett Evans.
My name is Cindy Rocha. Noemi Alanis.
I'm going to hand it over to Chiali.
So for the main goal of the lunar module habitat is to support long-term human presence on the moon for scientific research. And we also wanted to be able to survive extreme lunar conditions such as thermal and radiation. We also need to be lightweight for launch, and then stay strong after deployment. And it must also like be safe and efficient.
So why is our project important? As we heard yesterday from guest speaker Heidi Paris, Artemis project through NASA is making a lot of progress in establishing a sustained human presence on the moon to kind of study and get more of an idea of how we can continue to progress in space and make it all the way to landing a human on Mars. So the importance of our project is creating a place for astronauts to be able to actually stay long-term to study the environment on the lunar surface and get as much knowledge as they can possible to prepare for that eventual mission to Mars. So yeah, our project is just for like a step within the step to get to Mars.
So our main objectives is the total mass of the metric tons we went with is 4. We have right now is 4 metric tons. It's which meets the requirements. So the surface area for the lunar module is 50 to 80 meters squared. It provides extreme temperatures for -130 degrees Celsius to 120 degrees Celsius for extreme temperatures. It ensures radiation protection for the crew's safety and enables fast assembly time, which should be under 30 days. It supports power which is 5 to 20 kilowatts, and includes an airlock and safe entry. And since we're like the first semester here, this is our conceptual design. We initially designed this piece right here, as you can see, the airlock and the 2 floors with the legs. We explored like different ideas for each concept was evaluated based on the mass, strength, and the safety of it. It had rigid structures. We compared rigid with inflatable systems, which the rigid structures were more heavy and like too to like transport. With the inflatable system, it was like lightweight, and an inflatable module design was selected due to the efficiency and adaptability. The design was refined with multiple iterations.
Okay, so when we get into our design module, we took inspiration from the Lockheed Martin, as you can see like on the left-hand side, as our external inflatable habitat. And then as you see on your right-hand side, it is our like final or semi-final for our first semester of like the actual interior structure of the actual lunar habitat. So the idea is, to have like an external inflatable habitat as well as like an inner shell, just like as a safety net, right? You can never be too safe. As for our shell design, we do have 3 stories. Our first story, you have like this little bottom, but it's for storage, this little top of the hemispherical structures, or like caps. Is the bottom is for storage, and the top is for like communications. You have like a little hatch on the top, and then we're gonna have solar panels on top. The first level is going to be for like airlock and lab, and then the second and third are going to be for usable living floor space. Our surface area was met from the 50 to 80 meters squared, as Garrick mentioned. So this actual diameter is 8.5 meters, which gives us a surface area of 56.75 meters squared. And then for our simulation analysis, so in SolidWorks, we tried to, do the full-scale design. Unfortunately, SolidWorks freaked out on us and was like, hey guys, it's a little too big. And so we scaled it down to a 10% of the model. And by scaling it down, it actually decreased the thickness in the walls. So it looks a little buckly and like not as robust as we would want it to look like. But whenever it goes to like the full scale, it'll definitely not look as poofy. So for the inside, we did a stress analysis based on the internal pressure. So the internal pressure, as like you would want to like humans to live on, like the regular atmospheric pressure here is 1 atm, right? And so that's like a really high pressure concentration like on the actual shell itself. So NASA has like a standard for human survival pressure, which is 34.5 to 103 kPa for long duration like habitability. And so we went with 60 kPa, and it's going to have a 30 to 34 percent oxygen concentration that is safe for human habitability.
For our materials, we wanted to prioritize both safety and performance. For the inner shell, we chose carbon fiber because of its high strength and its low weight, and it's also cheaper than aluminum. For the outer shell, we picked Kevlar because it helps resist radiation and protects us from impact and tearing. And for the insulation, we picked polyurethane foam because it provides good insulation and internal support. Together, all these materials form a strong layer system designed to combat the harsh living conditions.
And then to go more in depth into our structure, we're using a lattice structure in between the flooring and the walls of the structure. It's lattice structured with trusses in the middle. We're going to fill in the middle with polyethylene foam for more insulation on the inside. And then it'll be layered, like he said before. On the inside, it's like helical design performance. It performs well under compression. And then these are more specifications on our material properties, showing our density, showing our tensile, yield strength. Kevlar we picked because all of these we picked because they're lightweight. Our goal of this was to do it as light as we can because it's just the habitat. It doesn't include any of the things inside it yet. So the lighter, the better. And then system features, we talked about how the outside later is gonna be inflatable. Interior, we're gonna have 2 floors that are livable. Airlock system for safe entry and exit. Structural pattern, which is our lattice pattern. Our materials as well. Our radiation, we went with Kevlar specifically because it was cheaper than dust mitigation. We are using indium tin oxide, which NASA's testing in order for it to repel the dust, which I know is a problem on the moon specifically. We're going to be using Starship to take our crew and our habitat to the moon. And then we're going to prefabricate everything on Earth and test it on Earth as well, so we know we can just put it on the moon and nothing should be going wrong. And then our power source, since we already have it, we'll be using solar panels.
Our manufacturing process focuses on the efficiency and reliability of the module. The module was built and partially assembled on line using advanced materials. It's then packaged into the compact in the Starship, which we're using to meet the launch constraints. The system is then transported to the surface, lunar. After landing at habitat, which would then be used in the inflatable, expands and complete it. The goal is to complete the setup under 30 days.
So for our future work, as we mentioned earlier, this is our first semester. So a lot of our design currently is conceptual. A big issue we kind of ran into when starting the design process was the fact that we were given a lot of creative freedom, and none of us in our group are like space experts or anything, right? So we didn't really know where to start. So the goal for our conceptual design was to kind of just make sure that something exists, and then spend a lot of our second semester refining the systems that we currently have, maybe reiterating them, redesigning them, which has been really beneficial to be here and like talk to all the other teams. It's been really interesting to see all of your designs as well, but just to kind of see like what problems we're missing, what we're not seeing it through different people's perspectives, and getting that feedback from these like-minded students as well as the mentors here on how we can kind of refine our design and keep it going for next semester. Some things we're considering is like origami-inspired internal structure. So with that inflatable design, we kind of just want to keep it as lightweight as possible, as Cindy mentioned earlier. So the goal is to have it collapsible whenever it's sent on the rocket ship on Starship 2 space, and then have it expand upon landing. So having origami-like structure where it can collapse before it's expanded on landing would be beneficial for cargo space as well as fuel use. And then considering landing, currently we have in place our like hydraulic cylinders and a ball and socket joint as for like the feet, so that way it can adjust to any kind of rugged terrain it would be landing on. And then we also ran into some issues just with our hydraulic cylinders, not issues necessarily with simulation, but just talking to other people here, kind of seeing the feasibility of that working in space. So those are things we're also considering redesigning or refining going into our next semester of this work. And then more depth in material testing as well as FEA simulations through our SolidWorks model.
So in conclusion, we're able to present a practical and innovative solution to life on the moon, combined with the inflatable skeleton and the 2 layers per layout. We can definitely improve the design later on because it's our first semester. But we're able to make it so it could combat harsh lunar,
We'd like to sincerely thank our advisor, Professor Raj, and then our other advisor, Dr. Peel, and then our senior design professor, Dr. Grady, throughout our project, giving us guidance, mentorship, and like a way to go, just because, again, it's really like the stresses. It is our first semester, so like it's a lot to take in, and just like to apply it to our following semester. And then gratitude to our NASA mentor, Robert, and Nina, too. Thank you for your help with the TSGC. And yeah, thank you everyone for making this possible.
We have time for a quick question.
Have you done a structural analysis for load on the floors?
The only thing we've conducted so far, we were focused on pressure testing, like overall shell, so we haven't done like an individual analysis of each floor.
Okay, thank you.
Hey, what constraint about the lunar environment as you guys are going through your design surprised you guys the most?
What didn't really? I did think like, we're so used to Earth, you know, there's nothing we know about being in space. I think whenever we initially started, we were kind of more focused on like the interior. We had to shift our design because at first we were like, where are we gonna put the toilets? Where are we gonna put the exercise machines? Like, how do they even use toilets in space? But after we kind of like refocused, we more, I think our concerns were like how to get it to withstand the temperature variations, especially since it's gonna be exposed to 14 days of a very high or low temperature, as well as like the lunar dust. Being here, at least talking to like everybody else about lunar dust, I don't think we realize how like harsh it really is. We've had a couple of design groups previously present like similar, not similar projects, but projects where they had to mitigate lunar dust issues as well. And so just like realizing how abrasive and like invasive it actually is, I think that's something we're really reconsidering for next semester, especially for the airlock system, is how to mitigate the dust like just from getting absolutely everywhere.
All right, thank you, Javelina X. All right, our final presentation this morning is from Texas Women's University, Team Mercurians.
Hello everyone, I know it's just about lunchtime, so we promise to boot this up quickly. We're Texas Women's University's Team Mercurians. I'm Gabriela Powell, and here with me are Candela Fidalgo Garcia, Natalie Vogel, and Austin Travis. We'd like to thank our faculty mentor, Dr. Blong, and our NASA mentor, Dr. Reyna. And today we're presenting our project, a pneumatic device for mitigating muscle atrophy in lower extremities during long-duration spaceflight. we may not pay attention to because we're so used to it, but gravity constantly loads our musculoskeletal system. This loading helps maintain our muscle mass and neuromuscular function. However, in microgravity, our body weight is removed, which unloads our posterior muscles and reduces our neuromuscular activation. As a result, astronauts can experience rapid and dangerous muscle atrophy, including decreases in protein synthesis, reduction in fiber cross-sectional area, and declines in force generating capacity. More severely, these changes can happen within weeks, which makes lower limb muscle preservation a major challenge during long-duration missions. Within the lower limb muscles, the soleus is especially affected. The soleus is the primary plantar flexor, and it plays an essential role in posterior stability and forward propulsion of the body when walking. Research shows that the soleus can lose up to 40% of its muscle mass during a long spaceflight mission. This loss can reduce postural control, limb mobility, and increase injury risk when astronauts return back into a gravitational environment. Another important muscle is the tibialis anterior, which is the primary dorsiflexor. This muscle is also negatively affected in microgravity, including a loss of fiber integrity, particularly in fast-twitch muscle fibers. Weakness of this muscle can lead to foot drop, which reduces balance and increases fall risk. Because of that, preserving activation in both the soleus and the tibialis anterior is important for protecting lower limb function in astronauts. One way to activate these muscles is through plantar mechanoreceptor stimulation. Plantar mechanoreceptors are sensory receptors located on the bottom of the foot. When meaningful pressure is applied to these regions, they can promote muscle activation in the lower limbs. This means that if we can strategically stimulate the sole of the foot, we may be able to get activation in muscles that would otherwise be underused in microgravity. One possible solution is by applying a pneumatic system. By using air pressure to drive pistons, we can apply repeated and localized pressure to activate these muscles. And we can make this even better because our device is individualized to meet the specific needs of our astronauts. This pressure will then stimulate foot mechanoreceptors and will help maintain lower limb muscle stiffness and muscle tone. So here's a summary of our problem. Microgravity induces atrophy of lower limb musculature, impairing strength, increasing risk of injury, and compromising mobility such as walking and standing. Our solution is a passive device that stimulates foot mechanoreceptors via pneumatic pressure to enhance neuromuscular activation and preserve lower limb muscle mass.
Our project is built on work done by a previous Mercurians team at TWU who created a boot that used two inflatable airbags placed under the forefoot and the heel. Their device mimicked a heel-toe gait pattern and stimulated plantar mechanoreceptors at the sole of the foot. However, their design only focused on the soleus and targeted more general areas rather than specific mechanoreceptors.
We named our device the boot, which stands for Therapeutic Heel-Toe Exosystem for Biomechanical Oscillation and Overcoming Tissue Atrophy, the boot. Our electrical components include an Arduino Uno R3 board, two 12-volt relay modules, one 12-volt battery, and one ground force sensor resistor. The Uno board controlled timing logic and sent signals to the relay modules, then alternated activation of the solenoid valves, which controlled airflow to the pistons. The battery powered all 12-volt components, and the FSR allowed us to monitor force and pressure during testing. For the pneumatic system, we used an air compressor, an air reserve, 4 solenoid valves, and 2 double-acting pneumatic cylinders. The compressor filled the air reserve until it reached 3 bar, or 300 kilopascals, which allowed the solenoids to control airflow in and out of the pistons. 2 valves directed air into the cylinders to extend them upward, and the other 2 allowed air to exit so the pistons could return to neutral. This created the alternating heel-to-forefoot pressure pattern that drives the device. The control code was written in C++ using an Arduino IDE. To ensure the force of safety, our device included a force threshold of 100 newtons that, if exceeded, will stop the device to prevent discomfort or injury. The system was programmed so the pistons alternated every 2 seconds, which created consistent and repeatable stimulation tempo similar to the gait pattern while still allowing the pistons to fully rise and reset. In addition, the total system runtime was capped at 20 minutes, which is the recommended amount of time for astronauts to wear the boot based on current literature. After that, the system automatically shut down. The final variable is the force contact area used in the force sensor conversion formula. To quantify pressure output, we used a voltage divider formula to translate FSR readings into force values. The raw voltage readings were converted into resistance in ohms, then conduction in microohms, then force in newtons, and finally pressure in kilopascals based on the contact area of the stimulating platforms. This allowed us to monitor both force and pressure during testing and verify that our device was functioning within its intended range.
To support the engineering design process, we used SolidWorks to create 3D models of the major components of the boot, including the pneumatic piston, the force sensor, the relay module board, the Arduino Uno board, the 12-volt battery, and the solenoid valve. We also modeled the full prototype assembly, which allowed us to visualize how the pneumatic circuit, pistons, and foot contact platforms all fit together. Final design included form-fitting Velcro straps around the ankle, the heel, and the forefoot to limit unwanted motion and improve stability during use. To evaluate our device, we used surface electromyography, or EMG, which measures the electrical activity of muscles. Generally, increases in EMG activity are interpreted as increases in muscle activation. Electrodes were placed over the soleus and the tibialis anterior according to the standard Cinium protocol. 2 conditions were established for our testing. One with the participant in a seated position with the foot resting against the ground, and one in a supine position with the foot resting against a wall. For each condition, 3 trials were recorded, with the first 3 to 5 seconds serving as baseline. The boot was then activated, and EMG activity was recorded for the next 15 to 20 seconds. Here, you can see the EMG muscle activations on the computer screen in the background while the device is running. At the same time, force output was recorded using a force sensor placed between the heel, forefoot, and their respective platforms, allowing us to ensure that measurable mechanical input was produced during testing.
Our results showed clear activation of the tibialis anterior and some activation of the soleus, indicating that the boot successfully targets mitigation of muscle atrophy in lower extremities. Soleus activity was present, but the patterns were less distinct, likely due to crosstalk and signal artifact. Meanwhile, the tibialis anterior signals were the strongest and most consistent. Force measurements also showed very clear and repeatable patterns at both the forefoot and the heel, confirming that the pneumatic device successfully delivers alternating pressure to the foot. Force values reached 250 kilopascals, reflecting the force recommended for optimal results in current literature. And our device has introduced several key improvements. First, we increased the pressure applied by the device, which also increased the force applied to the foot from 110 to 250 kilopascals. Next, in addition to targeting the soleus, our device also targeted the tibialis anterior, broadening the potential impact of the system. And finally, we replaced the previous airbag-based approach with more rigid mechanical components. There are several important directions for our future work. We'd like to decrease the weight to improve portability of the device. We'd also like to integrate current NASA systems for more power efficiency. More long-term and intensive testing is needed as well. And finally, more effective sources of ground reaction force should be investigated moving forward. In conclusion, a device that passively stimulates mechanoreceptors of the foot via pneumatic pressure was created and proven to successfully activate lower limb musculature for the mitigation of muscle atrophy. We'd like to thank our acknowledged listed here for their support this semester. And we'd like to highlight one of our outreach projects from the semester where we collaborated with TWU's Adaptive Physical Activity class. Our references can be found at the QR code. Thank you. We're happy to take questions.
Questions? Really great job, guys. I have 2 questions for you guys. When do you recommend the astronauts use this device? And have you held any kind of human factor studies to determine the comfortability level and willingness for people to use this device?
Thank you. Very great questions. For the first one, yes, we have solid literature that shows that we should be using this device for astronauts about 2 times a day, preferably, for 20-minute bouts each time. And anytime they wear it should be passive, preferably during downtime, any kind of leisure time that they have. And for your second question, I'm sorry, could you repeat the second question?
Have you guys held any human factor studies determining the comfortability and willingness for people to use this device?
Oh, yes. So we haven't done any tests, but the previous literature has shown that that 250 to 300 kilopascal range of force that we were aiming for and did achieve is actually the optimal results for seeing that activation of the muscles while still remaining safe and comfortable. So, thank you.
Other questions?
I don't have a question. I just want to say your project's really tough.
Thank you.
How did you come up with the 100 Newton number for applied force? I think it was a safety requirement in code.
So at first, when I was coding, I had the force limit at around 30 newtons, which is very close to where our force threshold is at. I believe it's around 27.5, which gets you around 275 kPa, which is a good range between 250 and 300 kPa. So I just put it up to a good amount that if, obviously we don't want 100 newtons of force going into the foot, so I put it at a pretty high limit, but the program is safe enough that it won't go up to that force. It'll only deliver the amount of force that is applied from the air compressor. So it's a good threshold to have, but it's not totally necessary or used. It usually just runs for 20 minutes and then it'll shut off.
So this is, I guess, passive. In other words, it's just using the high sensor areas on the foot, the different areas. Would that lead to maybe exercising while I sleep? In other words, if this is something that can save them time instead of wasting 20 minutes exercising, is there any value to letting them get stimulated while sleeping, or will it disturb sleep? Because if I can save any time and get double bonus like exercise and sleep, that would mean a lot.
Thank you. Actually, our device is not meant for hypertrophy, so it does not replace the regular exercising systems. This is meant to be used outside of that exercising time during downtime specifically, since it's passive. We specifically targeted the mitigation of atrophy, so this is only slowing their losses. It's not built for exercising.
So right now you're working with a fairly small area, just a couple of muscles. Do you have plans for other areas of the body that you might be able to do a similar activity with?
We would absolutely love to continue to do more research looking at starting with other musculature of the lower limbs and then moving into other parts of the body. Yes.
All right, thank you for your curiosity.
All right, let's give a round of applause to everybody who presented this morning. All right, so those 13 teams that presented, you have one more task. You need to get your photos taken in front of the TSGC wall display out front before lunch. So Aaron, is Aaron out there already? Yes. Aaron's out there. Go see Aaron the photographer, get your photo taken. Then you can get lunch. Everyone else, go enjoy lunch. Enjoy the posters. We start back at 1:30.
right, good afternoon, everyone. Welcome back to the TSGC Design Challenge. The first team this afternoon is from Carlton, and they are Relish LTV.
Good afternoon, everyone. We are Relish LTV, and we are back again this semester with our next generation lunar terrain vehicle. This is our team, and starting from the left, we have Bram, Yash, me, Nick, Alyssa, Irving, and Samaya. This is our advisor this semester, Dr. Norda Sharifi, and this is our NASA mentor this semester, Mr. Chapman Lansdowne. Now I'm going to pass it off to Bram.
Thank you, Nick. So we'll begin with our background and foundational research over our lunar terrain vehicle and follow with a new LTV design, new LTV setup, new wheel and designs, testing results, and future considerations, and lastly, the conclusion. Our project focuses on designing a lunar terrain vehicle to transport astronauts and supplies on the moon. This comes with challenges such as strict weight limit, abrasive terrain, and as well as long-term reliability. Our design has key constraints such as safety, terrain adaptability, as well as having to withstand temperature fluctuation. Through our previous research as well as feedback, we've come to the conclusion of a 2,000 kilogram weight as well as a 800 kilogram payload capacity. I'll now pass it over to Yash to cover over the new LTV design.
Thank you, Baron. As you can see, this is our next generation LTV design. It is similar to our previous design in that most of the mechanical parts are 3D printed. This, however, includes a few new features, and some of those features include an actually remote control mechanism. We have new larger wheel designs. We also have a fully independent suspension, drive, and steering system. For a little bit of a demonstration, we've got and so this is the control itself. Upon calculations unloaded, this thing can go approximately 22 miles per hour. So we are meeting the minimums that NASA asked of us with the 20 mile per hour minimum. And with that, I will pass it off to Irving for the electrical design.
Thank you, Mr. Yash. So our lunar terrain vehicle incorporates a LiPo battery that's basically a lot more energy efficient and weight efficient as well. We've incorporated, or the core components we've incorporated is a solid state relay, custom fused bus bar, and 4 electronic speed controllers, which is then connected to each motor, and each motor is connected through a Hall effect sensor. No, sorry, excuse me, a servo motor, and that helps with the independent steering. Additionally, we've added a 5th circuit for the lighting module system, and together, all those components that we've chosen help with the longevity and the electrical efficiency of our lunar terrain vehicle.
Thank you. So these are our new wheel designs for this semester. We added a chamfer to increase surface contact while turning, improving maneuverability. Inspired by design 3 from last semester, the slant wheel showed the least amount of sinkage but had the least amount of traction. This was our best performing design from last semester. The hex with no ridges showed less regolith retention but struggled at slope testing. Based on feedback from our NASA mentor, we added tread-like ridges to increase traction, and overall it worked. This was our strongest performing design from this semester, but is on the heavier side. The aero wheel features ridges along with aero cutouts to increase traction and reduce regolith buildup. Although it performed well, it has multiple weak points in unsupported areas. Now on to RFA.
With our new calculated normal and friction force, we conducted different types of FEA. So the idea is the wheel is built out of two materials. The inner hub is made out of aluminum 6061 and the rest is made out of nylon. All the FEAs passed and the maximum stress was under the yield strength. For stress, displacement, and strain, the slant will perform the worst with the highest value, where the hex width ridges perform the best with the lowest values. We also conducted different thermal FEAs to see how the materials work, and it only failed going from negative 250 degrees Celsius to 127 degrees Celsius at the hub. So if the LTV plans to stay up there around the pole for a longer time, the hub should be made out of titanium instead. We also conducted dynamic FEA, and even with a really high torque, it was under the yield strength and had a great displacement as we wanted it to.
Moving on to our testing, this semester we used the same test bed as last semester due to our prototype not being able to entirely fit. Each wheel was tested individually with our new test apparatus, and we used an electronic speed controller, ESC, to control the RPMs of our motors. And here's some sample footage of each test. Going through our time testing, you can notice that each of our wheels do traverse the test bed pretty quickly in roughly about the same amount of time. Moving on to some sample footage for our slope time testing. A couple things to note here is that our wheels without the ridges do struggle to get over a 20-degree incline, especially the slant wheel, it digs in here pretty well. And then our wheels with the ridges are able to overcome that 20-degree incline relatively quickly compared to the ones without ridges. Moving on to our force and sinkage testing. A couple things to note here is that our wheels without the ridges do not dig as aggressively into our simulated regolith as the wheels with the ridges do. Moving on to our results from our testing. Each test was conducted 5 times, and then the average is reported here, and then the error from that average to standard deviation error is shown. First up, we have our energy test. Basically, when we were doing our time testing, we realized that all the wheels were relatively the same time, so we came up with a different metric to differentiate the wheels, and that was with how much energy it consumes to traverse the test bed. And as you can see here, the wheels without ridges do consume less energy to traverse the test bed. Moving on to our force and sinkage testing, we came up with a force-sinkage ratio. So we took our force and we divided it by our sinkage. So a higher ratio means the wheel performed better. And as you can see here, the wheels without ridges did perform better with a higher ratio. Moving on to our slope time testing. As you can see here, our wheels with the ridges did perform significantly better than the wheels without the ridges due to it being able to apply more friction force to get over the slope. And then finally, we came up with a final decision matrix to clearly show which wheel is the clear winner here. And as you can see, hex with ridge is our clear winner with 15.4 points. Now we're going to go on to our test errors.
Thank you, Nick. When it comes to testing errors, in comparison to our previous semester and the prototype of then, we were able to actually minimize many of those testing errors. When it comes to the inconsistency of the quick mix and its effect on the traction of these tires, we were able to minimize that with the larger contact patch that these larger tires do have. Whenever it comes to time testing, we unfortunately were not able to construct a timer to automatically start and stop the motors, so we unfortunately could not minimize the human error that came with time testing. But for force testing, we were able to mitigate the inconsistency with the force data by optimizing the structure in which we applied forces to our force gauges, pushing instead of pulling with the string, which would then angle the string and cause tension in multiple axes. For the non-ideal setup for force testing, again, it helped that we created a slightly more sturdy setup compared to previous, and in terms of in terms of pebbles affecting the force testing, that also came down to the larger patch size that these larger wheels give us. in terms of future considerations, what we wanted from last semester to now, we were able to get the majority of them, as you can see. We were able to manufacture better debris shielding. We had TPU covers that we screwed on. We weren't able to make a bigger test bed, unfortunately, but that is for next semester. We were able to incorporate slope testing for each wheel, incorporate dynamic FEA solutions, simulations, as you guys can see or saw. We have better suspension for the prototype. We have a better wheel motor and wheel hub motor for each design. We also have some weighted testing with the LTV to get some quantitative and qualitative testing to figure out which design would operate under load. And we were able to incorporate and manufacture a multi-material design into our wheels as well. One new consideration that we would like to have is to have an even sturdier apparatus so that we can add more weights and truly test each wheel design. And so with the conclusion statement being that the hex with ridges is the most favorable according to our decision matrix and overall. Next, we will be focusing also on the suspension development of our LTV design. With that, we would like to thank the TSGC, NASA, and our mentors to making this all possible. Now, do you all have any questions?
Questions?
So I see y'all have done some great looking testing for each individual wheel. Have y'all done any testing with the whole LTV as a whole, or is that just waiting until y'all get a bigger test bed for that?
Currently, we are trying to test each mechanism separately, and then we will put them all together into one true and final LTV design. So for right now, we are just focusing on the wheels and wheel design considerations. After that, we will, as we've shown before, we'll be focusing on more development of suspension. Then from then on, we'll move to more optimized chassis design and so on and so forth until we have a full LTV design that will be competent. Okay. Thank you.
Question?
Hi, do you mind going back to your very first FEA slide?
Yes.
Yes. Okay, so this is static analysis?
Yes.
Can you describe the loads and boundary conditions that you imposed on this model?
I can explain that. So we basically calculated the 2,000 kilogram weight that's like a regular required for the LTV. What we did is we, of course, considered the 1/6 gravity of the lunar surface. After that, we calculated 1,184 to be the normal force and 689 to be the friction force. And all of this has friction force and normal force over here, and it's fixed in the middle. So when the motor is going to rotate, it's going to be fixed in the middle, but the force is on the wheel. For each design, you can see on the displacement, all of them reacted differently for the force, even though it's the same force at the same place.
Yeah, thank you.
Yes.
For these FEA results, did y'all account for the wheels being bigger in an actual final rover?
It's actual size.
Yes, they are actually scaled up. So the current models are 1/5 the size, and then we scaled them up to be the normal size by 5 times.
Other questions?
You talked about how time didn't end up being a good measure of performance. And then you introduced something called force of how you measured the force and the sinkage in your test setup?
Yes, so basically, when it was sitting in the apparatus there, we had our force gauge attached to the apparatus on one end, and then to get a more rigid body, we pushed the apparatus into the force gauge, and then we measured the sinkage after performing the test for exactly 3 seconds.
Sinkage of?
The wheel is...
The outer wheel into your
yes.
simulant?
Yes.
Measure how?
We measure, so on the one side of the test bed, there's a clear acrylic panel.
Mm-hmm.
And basically what we would do there is we would get basically down eye level with it, and then we would measure it with a ruler. Basically to like the nearest decimal place in centimeter wise.
So I see that you've gone with a combination of the hex and the arrow, is that correct? As your desired final one?
Hex with ridges.
Yes, hex with ridges. And did you find that there was any difference between forward or backward rotation in comparison with your ridges?
Yes, so especially during the sinkage testing, depending on which way the wheel was facing, it would aggressively dig into the regolith more. If it was moving backwards, where it's going into the back arrow point of the ridge, it would be basically like shoveling the simulant instead of kind of digging in and then kind of pushing it out like the other way as well.
Very good, thank you.
Thank you, Willis. All right, our next teams is University of Clear Lake, Office of Lunar Affairs.
Hello everyone, we're the Office of Lunar Affairs and we're here to present our proposal for the lunar surface habitat. My name is Cole Curtis. I'm here with Calvin Rampy, Silas Anderson, Eric Molina, and Andrew Tomlinson. During this presentation, we're going to cover the project goals, the target criteria and constraints, the modeling and analysis of our design, the technical content behind our design, the prototyping, the testing we've performed, the testing we plan to perform, and any forward work. The project goals for our proposal are to provide lunar missions with a modular, durable, and manufacturable surface habitat. These habitats need to support long-term stays in harsh thermal and radiation environments and be functional up to at least 15 years. The design needs to overcome construction and logistical challenges on the moon. They need to address structural, thermal, and radiation constraints while still adhering to mass limitations. And the design needs to be scalable to support human long-term stays on the surface of the moon. This table represents our target requirements given to us at the beginning of last semester against our final specifications we have at the moment. Two that I want to point out are the weight and the usable area, specifically because this is where we face the most challenges. So the area we're looking to habitat is the south pole of the moon, And we are suggesting that the habitat be placed strategically, like in this picture, to help support radiation protection. The transportation we plan on using is the new Glenn rocket. We originally wanted to use the Falcon Heavy, but after last year there were a few successful tests with the new Glenn, and it has a bit of a larger fairing by about 2 meters and allowed us to have a larger floor space for our habitat. And I will pass it off to Silas for the technical part.
Thank you, Cole. After receiving our design constraints, one of the first things we did as a team is we generated a high-level functional decomposition, thinking about the energy flows, the mass flows, and the signal sort of required. This kick-started off our brainstorming process, and we generated a bunch of different ideas, from mobile habitats to excavators that would carve out regions on the South Pole, and a bunch of stationary habitat concept designs. And we took all this feedback to our mentor, and he gave us a lot of valuable input, and we crossed off a lot of designs that NASA wasn't really interested in, and took that feedback and churned through a series of decision matrices, culminating which is our final decision matrices, which yielded our solution to our proposed solution to the Lunar Design Challenge. And I present to you the Hawk's Nest. The Hawk's Nest is just under 10.5 meters tall, 6.31 meters in diameter. It's 3 stories, and it is a stationary, inflatable structure supported by a rigid internal superstructure. We met our mass requirement just barely. Our mass requirement was 10 tons, and we were just at 9,999, so it's pretty cool. And we met our assembly requirement because our intent is that it's going to be fully assembled here on Earth. And as far as the inflatable portion, we plan to have a little bit of air initially in the habitat, so that during travel, the gas will expand to the total volume amount, and then when astronauts, so the capsule will be sent up first, and then when astronauts are sent to live in the habitat, they might bring some extra air so that there can just be more clean air to circulate. Some of the construction highlights that I'd like to point out is that the inflatable portion of our design took a lot of inspiration from NASA's already existing ISS beam module, and that is basically a bladder fabric component, which we'll go into more detail a bit later. The internal structure, we bounced back and forth between a few different materials, and we ended up settling on a composite carbon fiber. And this should throw a little bit of caution in, because there are a lot of useful properties for composites, but they are a brittle material. And so in order to demonstrate our rationale and show prove our judgment for choosing this, we'll go over that into more section. But when it comes to material selection, we followed all of the NASA applicable constraints and their guidelines. And to go into more detail on some of the specifics of our analysis, I'm now going to pass it off to Andrew so we can go over those components.
Thank you, Silas Anderson. Our structural support assembly consists of I-beams, shown in yellow, a floor sheet that rests on top of the support assembly, support rings, shown in red, green, and blue, pillars, which are the thin tubes around the perimeter, and a central column, the large tube in the center. For our solid mechanics calculations, we considered the worst-case scenario where the first floor suffers an emergency depressurization, but the second and third floors remain pressurized and loaded. Under this scenario, the weakest component is the floor sheet. However, under normal loads, the weakest component is the central column. This is due to the weight of the structural system. The difference between the weakest component for worst case and normal case. So in the codes and standards we applied to this project, 100 pounds per square foot of distributed load, a factor of safety of 2.0, 2 remote emergency exit paths. This is the reason for the third floor emergency exit airlock and the 2 ladders on the opposite sides of the habitat from first floor to third floor. For our structural testing of our assembly, NASA's standard is to go to a proof test factor of 1.5 times the design floor loads. However, we will be going to 1.75 times the design load because we do not want to go to jail because it's a code. This will be done in quarter steps every 10 minutes. There should be no rupture, fracture, or residual deflection after load removal. Our power distribution plan distributes 5.5 kilowatts between 3 floors and an active thermal management system. The power outlets are shaped like smiley faces to improve astronaut morale. I will now pass it to Calvin Ramping to discuss the beam module.
Thank you. So, a brief overview of the beam module. The main reason we decided to implement this into the design of our structure was because it is highly lightweight compared to other traditional encasements for pressure vessels. It also offers many beneficial uses depending on the layers implemented in the design. So, the standard NASA design that's been test proven on the ISS has multiple layers within it, including a thermal and an outer bumper layer to protect against micrometeor impacts. That is something we looked into because if you're going to be living up in space, and especially a bubble-shaped contraption, you want to know, like, what's the likelihood that you're going to be hit by an asteroid? So we did a preliminary analysis over the span of the time this habitat would be placed on the location on the moon. The result that we got was as seen on the screen. However, after listening to our guest speaker yesterday talk about how the Artemis mission saw multiple impacts on the south pole of the moon, we have realized that this may not be 100% accurate, and so we will definitely be going back to re-look into that. However, the beam module does incorporate an outer bumper layer to kind of essentially as a protection mode against those micrometeors, and is designed to stop anything traveling at a hypervelocity of 5 to 7 kilometers per second. We also looked into a depressurization event, just in case there was a puncture event that were to occur. What's the safety procedure for astronauts to take? And so we did a depressurization analysis based off of varying hole sizes, ranging from 1 millimeter to 1 centimeter squared. The result, the red line on our graph is shown, is basically anything beneath that is the point at which you would be unconscious because of the pressure in the vessel. So we looked at the time frame, and essentially for 1 centimeter squared hole, which is the size of a hole punch, you have roughly 30 minutes to react, whether it's patching, putting on a chute, or escaping to a different floor, because this analysis is particularly only based off of 1 floor, not the entire depressurization of the habitat itself. So again, we have, our design is broken down into kind of 2 main components. We have a CFRP frame, which consists of the I-beams, the inner, middle, and outer rings, a central column, and the pillars. We decided to implement those rings as kind of a later design concept because of our circular design floor, we're going to have a lot of that bending within those spans in between each I-beam, and those have shown through analysis to be a reinforcement of a structural stability. As far as our dome, we have a different material that we're using. We went with a high-strength molecular polyethylene, and then we have our titanium hook points. We were asked to incorporate this into our design as to how you would lift our habitat, and so we designed it based off of like a basic inspired lift point used in infrastructure nowadays. This is made of titanium. There are 6 of them that will be represented across the top of the dome, tangential to the curvature, and these will not only be used as a way to lift our habitat, but they will also be able to be used as anchor points after the habitat has been transported to the surface of the moon. As far as prototyping, we did two separate types of prototyping. We did a test prototyping that we made completely out of CFRP. This is what we will be using to do further testing analysis and collect that data. And then we also went ahead and we did a prototype visual reference. This is entirely made out of resin printing because it was something we had access to, and it was something we could definitely scale up to a size that is more visually represented for our habitat. With that, I will pass it off to Eric to go over our FEA analysis.
Thank you, Mr. Papa. And now for the FEA study, so we're going to analyze the structural stress, and it will be done by applying distributing those on each of the floors. So it will be 100 pounds per square feet in a downward direction. So under these circumstances, it was seen that the structure did not fail. The overall structure remained under low stress regions. And it was seen that most of the stress was on the initial perimeters. So now for the FEA, we did it for the pressurization. Here we applied 14.69 psi under all of the internal surfaces, as well as a distributed load of 100 pounds per square feet, pointing down on each floor. So this showed that there were no critical deformations, as well as the structure was efficient under load distribution. Also, the maximum displacement was 0.5 millimeters, so the structure was stiff. So now to validate our material performance, we did a 3-point bending stress. We used CPR samples. Each sample was 6 by 1.2 centimeters. And the maximum applied load was 450 newtons in the center of the sample. So the FRP showed that the initial failure occurred at a maximum stress of 914 MPa, while the structural stress was at 48.7 MPa. And now for a prototyping ratio testing plan, we plan to do our compression testing as well as our hydrostatic test. So the first floor will go under the compressive testing, and then the hydrostatic testing will be to simulate the pressure. Now for the bill of materials, most of our costs were due to the CFRP, the resin for prototyping, or CFRP for the central rod, as well as the floor design. The total cost was 526.16. Our references. Any questions?
All right, thank you, team. Unfortunately, you ran out of all your time. Let me just double check though, is Pioneer 39 here? If not, we've got extra Okay, our next team from Texas A&M is Team Daedalus.
Howdy, we are Team Daedalus from Texas A&M. I'm Sarah, this is Matthew, Drew, Amod, Matthew number 2, and Cody. And we've designed a lunar drone that uses electrified regolith as its form of propeller. So this is our first semester participating in NASA's Orbit Challenge, which required us to design a solution to one or more of NASA's civil space shortfalls. These are mission-critical technology gaps. Our lunar drone is a solution to 2 of NASA's shortfalls: developing propellant out of lunar resources and maintenance of lunar infrastructure. Traditional drones rely on air to create lift, but the atmosphere on the moon is too thin to support air-based propulsion. So our drone needed to use a physical propellant source. By developing this propellant out of the lunar resource, we solved the first shortfall of our design challenge. The second shortfall of our design challenge is maintenance of lunar infrastructure. Yesterday's speaker gave some amazing background into the Artemis missions and the base that we're going to build on the South Pole. This base is expected to have structures reaching up to 15 meters in height. Our drone is capable of reaching the top of these structures and performing inspection and maintenance there. Additional use cases of our drone include resource collection and sampling from permanently shadowed regions, as well as surveying, terrain mapping, and transport. In this first semester of our project, our objective was to select the propellant source, design critical systems, and prototype and test our propulsion system to determine its feasibility.
So as Sarah already mentioned the first 2 design goals, the ones that we really want to focus on here are using propellant source from the lunar resource, because that maximizes NASA's in-situ resource utilization program. And we also want the entire drone to weigh less than 3.5 kilograms, so we don't need as much energy to power the entire thing. Looking at the decision matrix here, you can see we have 3 viable options: cold gas, lunar regolith, and hydrogen peroxide. Coal gas and hydrogen peroxide can both be derived from water ice, but water ice is only found using PSR, so it's really hard to obtain. Lunar regolith, on the other hand, is everywhere, super abundant, super easy to extract, and that leads us into triboelectricity, which became the next big propulsion method for us because of the efficiency and reliability. So I will quickly demonstrate why I'm holding a balloon. If I run the balloon on this poor man's head, you can see the static allows the hair to stick to the balloon, which is the most fundamental source of triboelectricity. Triboelectricity, simply putting, is just the transfer of electrons between 2 objects that come into charge here. The entire point of the propulsion subsystem was to triboelectrically charge the lunar regolith so that we can send it through an electric field at the bottom of the tube. The white arrows represent points of contact, and the black represents the actual regolith molecules. The white arrows are pointing to aluminum, which is where the electrons actually transfer because of the triboelectric properties. And due to the multiple points of contact and the angle of decline from the actual aluminum, we can prolong the contact and maximize the result of the triboelectric effect, meaning we don't need any additional power to power the regolith. And just to make sure everything is fluid, we have vibration motors posted outside of the triboelectric chamber to make sure nothing gets stuck. And we have PTFE insulation tube outside everything just to make sure all the contact is grounded.
So this is an animation that we've created to demonstrate the movement of regolith in our triboelectric system. So initially it begins in the auger feeder, and it falls into the triboelectric tube where it contacts various stages and accumulates charge. It then falls through the electric field generated from the electrodes, and which allows it to accelerate out of the thruster.
In order to accelerate the regolith, we have to pass it through an electric field which we generate through an electrode system. We attach a power supply to the top of the electrode system, which creates a voltage gradient, which creates an electric field, which we can accelerate the regolith through. One of the main novelties of our design is the use of a multi-stage electrode design. Instead of using one giant voltage gap, we have a bunch of small voltage gaps electronically isolated from each other, stacked on top of each other to generate the same thrust with less voltage. Kind of breaking down the theory and getting to the equations, we can use conservation, momentum, and energy to find that we need 15 electrode stages at 10 kilovolts to support hovering on the moon.
The top of our drone is going to be hollowed out so we can store regolith into, which will feed into the 2 holes which will go right into our auger feeder system. Our auger feeder system goes into 2 triboelectric chambers that lead into 2 gimbal thrusters that can angle to stable the drone as needed. Also, all the materials chosen for the drone were chosen based off strength to weight ratio, cryogenic properties, and abrasion resistance.
Our drone uses a hopping approach to movement over any steady stream due to fuel efficiency. It begins in the launch stage where regolith mobilizes in the triboelectric system to provide that initial thrust. As it reaches the maximum height of the hop, it redirects itself onto its desired path, and as it coasts down, it activates sensors that allow it to detect the rate of descent as well as the distance to surface of the drone. And lastly, the main thrusters are reactivated in order to increase the propulsion for another hop.
Our drone has several use case variants, including a surveying and collection variants. Both these models will have cameras to allow for visual inspection of the lunar environment, including structures and terrain, and the collection drone will have robotic arms to allow for maintenance and collection purposes. The main goal of our prototype was to test the feasibility of using regolith as propellant. With this goal in mind, we needed to build an experimental setup that could test how much charge we could accumulate in the regolith through our triboelectric tube, and build a circuit design that could simulate the electric field to accelerate the regolith through a set of electrodes. With this, our prototype is broken down into 3 main parts: a regolith feeder, triboelectric tube, and electrode accelerator. The regolith feeder was prototyped out of a 6-volt N20 motor connected to a drill bit. This turns rotary motion into linear motion and allows for precise mass flow control of the regolith simulant. This leads into the triboelectric tube, which is prototyped out of PLA and aluminum foil. It has 8 stages to allow for 8 collisions of the regolith simulant with the aluminum. We found that 8 collisions was the optimal amount of collisions for triboelectric charging. This triboelectric tube has vibration motors placed on the outside of it to improve the mass flow of the regolith through the system.
In order to charge the electrodes, we take 12 volts and put it into a DC-to-DC high power supply to turn it into 1 to 3 kilovolts, which we directly attach to the 4 electrodes. Due to the high voltage requirements of our system, we take a variety of safety precautions in order to make sure our circuit doesn't catch fire or any sort of concern happens. First, we implement a ball-type resistor in series with the entire circuit, which drops the effective current throughout the circuit. Then we have capacitors in parallel to each electrode, which create a low impedance path for charge to go through instead of arcing between the plates. And then we have a discharge resistor in parallel to the entire circuit, which discharges the whole entire circuit once unplugged.
We found that the voltage of our system was too high for a PCB, so instead we directly hardwired it onto our polycarbonate box that we're also using as housing for our electrodes.
The main objective of our prototype was to test how much charge our system is able to induce on regolith. South Pole lunar regolith simulant was split into 3 particle-sized groups, and a controlled amount was sent through our system. A digital multimeter was connected to the top aluminum step, and the voltage difference across the aluminum was measured before and after contact with the regolith. This allowed us to determine the amount of charge our system induces on 1 centigram of regolith.
So our results show that the actual size of the regolith is pretty significant to us. We can see that the smallest and the largest group of regolith didn't provide as much charge, but that middle range gave us the most potential difference that we needed. So we used this group of regolith to make our calculations and then decide what type of regolith should be fed into our regolith feeder.
Putting these numbers into our calculations, we found that we had around 0.03 microcoulombs per gram of resultant charge on the regolith after passing through the triboelectric tube. This is enough to support our previous calculations and the hovering calculation that we did for On the Moon. Additionally, we did experimentation with the entire setup where we generated around 3.76 millivolts or millinewtons of thrust at 64 volts, meaning that if we were to extrapolate that up to 10 kilovolts with the 15 stages mentioned before, we would be able to reach up to 15 meters.
Future semesters would include obtaining a Faraday cup to more accurately measure the charge of the regolith, implementing a radioisotope thermoelectric generator that utilizes the half-life of plutonium-238 to provide constant heat to the drone, and coding sensors to more efficiently stabilize the drone and code chart flight paths.
To summarize our project, we satisfied our first shortfall by designing a novel propulsion method that uses electrified regolith. This resource is abundant on the moon and doesn't require complex processing for our system. We satisfied our second design shortfall by designing a drone around this propulsion system that's capable of inspection and maintenance of lunar infrastructure. Through our prototype and testing, we were able to prove the feasibility of lunar regolith propulsion and determine that our drone can produce thrust to fly up to 15 meters. Beyond inspection and maintenance, our drone has a wide variety of use cases that increase NASA's mission capabilities for Artemis and beyond. Thank you for listening to our presentation. We've provided links to our references and our experimental results, and we're happy to take any questions.
Really great job, guys. It sounds like your system uses quite a lot of energy. Have you guys thought about the lifetime of your guys' drone, like how long you'd be able to propulse, and also how you would recharge that system?
So one system that provides energy mitigation is the triboelectric charging itself. The way that we charge the regolith doesn't require any sort of power supply because it uses just the material property of the aluminum to transfer charge to the regolith. If you want to add.
Yeah, then for our electric accelerator system, we're operating at like very, very low power ranges. So the current flowing through our system is like in the microamps. And so there's very, very little power consumption as we're flying. And so theoretically, it'd run out of like juice with the regolith before it would run out of the charge from the battery, which you could just recharge like back at the lunar base or something like that.
Other questions?
So I don't know whether it was just a picture just to show, but it looked like you were using like a flute multimeter to try to measure the voltage that was generated across by the electrostatic effect. Is that true?
So the multimeter that we used was acquired from our university lab. It's called the FEDC. And yeah, we used the multimeter to measure the voltage difference across the aluminum.
So that one?
No, that's just a picture of the multimeter. That's not directly the one that we used.
Yeah, there are better multimeters for that. But the other thing is, once you get the electrons onto the aluminum, where do those electrons go?
So the outside of like our housing is grounded, and so we're gonna implement like a neutralization system. So once the drone lands, all of the charge that kind of builds up on the aluminum, that kind of builds up on the outside of the drone because the aluminum is connected to the outside of the drone. So once it lands, we have a neutralization system that removes all the excess charge from the system and puts it into the ground.
Yeah, I'll add on to that a little bit. So we've done some preliminary research into that. We want to do something like a conductive grounding system where we have like various nodes around the drone where we kind of like draw the charge to and then take care of it that way. We're also looking to other opportunities like corona discharge. We're looking to other opportunities like that. But for now, that's like what we're planning to do in our future to improve the drone.
Any other questions?
So I believe in your concept map you mentioned a auxiliary thruster that you would use to kind of steer during the hopping. What would your propulsion be for that auxiliary thruster? What propulsion do you think you would use for that?
Sorry if that was a bit misleading. Our drone only uses the two thrusters that we have. The mechanism for like controlling tilt and turn is the fact that the two thrusters are gimbal. So our system is able to fly using only electrified lunar regolith. There are no additional gas-powered thrusters. Sorry if that was a little misleading.
I might have misread it.
What size are you talking about for this? I didn't see dimensions for anything.
So our test results proved that we can provide thrust up to 15 meters of a 1 kilogram drone. However, this result is scalable. By adding more electrodes, more propulsion system, and more regolith, we can scale it up to 10 kilograms or even more.
So the entire point of the prototype is just the feasibility of triboelectricity. So with the actual prototype and everything is scaled up so we can present to the viewers how everything actually works. In reality, the electrodes on the actual prototype right now, they're quite big and quite heavy. In reality, the actual sheets, we wouldn't need an entire polycarbonate box to show everything, and everything would just be scaled down.
All right, thank you, Team Daedalus. All right, that concludes our first session for the afternoon. So our next session will start at 2:40. We've got about a 15-minute break. welcome. Our next team is from UT Tyler, and it is Team Lens.
Good afternoon, my name is Julian Garcia. And I'm Rowan Brumont. And this is Team Lens, also known as Lunar Exploration and Navigation System. So our project is the integrated lighting and camera system. So it's me and Rowan, but unfortunately Tangina couldn't make it today due to a last minute family emergency. But we just wanted to give special thanks to our mentor, Ms. Clark, as well as a special thanks to our advisor who helped us along the way, Dr. Razak. So our problem is the current lunar imaging system produces inconsistent imagery due to its lighting variations, and its fixed setup cannot adapt to its changing conditions. So there's three key problems that most people need to fix on the moon. So it's no atmospheric diffusion, its fixed lighting fails, and navigation requirements. So that means with the atmospheric diffusion, without any atmospheric lights, the sunlight is basically unfiltered, so it's hard to really tell the shadows as well as the highlighted areas, because they both coexist on the moon. For our fixed lighting, any static lighting will basically be overexposed in specific areas and also underexposed. And with our rover, the rover cannot safely path around its terrain unless it's able to see. So our system needs to be able to not only be aesthetic but also a safety concern. So the three objectives that we wanted to focus on is create an adaptive lighting and camera system, design a mount to support all of our equipment, as well as achieve a measurable image quality to improve itself under high contrast conditions. So this is the CAD model that we have made. As you can see, it's 6 feet tall, it's 2 feet wide. We have 2 fill lights at the top and 1 navigation light down at the bottom. In the middle, we have our heat box, which is going to be storing all of our electrical equipment. And just on top of our heat box is going to be our 2 cameras. It's mid-frame and forward-facing. And our power bank that we use for testing is going to be sitting at the bottom, but when we attach it to the theoretical lunar rover, we'll be using the power from the rover. So this is a picture of our model. If you can't see in the middle, this is what it looks like. It's 6 feet fill light, so with its height being 6 feet and our angle beams at 10 degrees, it's able to be the center array lens for around 10.4 meters, just beyond the 8 meter specs that we were hoping for. So with the 2 feet navigation lights, it's able to handle 0 to 4 meter zone, where the tall fill lights basically create its shadow, keeping the ground directly in front of the rover always lit. With the horizontal spread of just 1 foot offset from its sides, we're able to have the 2 fill lights be 5 meters width with a 6 meter range, keeping that 1 meter overlap in place. So for our ground plane illumination maps, we have these 2 images. The first one here is generated through MATLAB. So with it, it's at 50%, and this second image is at 100%. So with the 50% image, the lux consort only reaches around 3 meters, whereas at 100%, it's able to reach 4.2, but if we were to go for 70 lux, it would be able to reach 3.5. So it basically double what we were hoping for. And with that, I pass it over to Rowan. Big dog.
So camera selection obviously is a very critical part of our design. When we started, we had 1 camera, and then we learned quickly that a single camera can't simultaneously output at full res and run fast enough to continuously feed back the information to our control loop. So we had to get 2 cameras. 1 camera is the IMX 477, which what its job is it takes the high quality pictures, which is the final image output. And the other camera, the IMX 708, is the one that's continuously running at low res, and basically its job is to feed the information from what it sees back to our control loop to tell it to control the lights and do whatever we want it to do. And for the IMX 477, that's the more important camera because that's the one that actually produces the final image. And so how we selected that is that we needed to know the specs. And so from NASA data, we found that lunar scenes reach up to about 256 to 1 contrast between illuminated areas and shadow craters, which is very high, and that translates to 8 stops. And if you don't know what stops are, basically it's a measurement that tells the camera how much light to let in, pretty much. And so we just added a 3-stop margin just to give us some wiggle room. And so our target was 11 stops, and as you can see, the IMX 477 has a dynamic range of 11.4 stops, which met our target, and it has a resolution of 12 megapixels. And so the camera the way it sees, it's split into different zones. The top part, as you can see, is ignored, and the reason why it's ignored is because the main purpose of this design is to be mounted on a rover for navigation and inspection, and really looking at the sky. Our lights are going to reach the sky, and the sky is going to, if we include that, it's going to mess with our values of brightness for our system and give us false results. So we ignore the top 33%. And we have 3 zones, even though it looks like 4 on the right. We have a top left zone, a top right zone, and then the 2 zones on the bottom are 1 zone. And they correlate to the different lights that we have. And the reason why we have different zones is because it doesn't make sense, for example, if in the top right portion, there's a lot of light, and in the top left portion, it's kind of dark. It doesn't make sense for both lights to turn on. We should keep the top right light off, and then the top left light should turn on. So that's the reason why we have different zones. This is the architecture of our software. Basically, the way the system works is you turn the system on. Before the lights or anything turns on, the higher resolution camera takes a picture. Then the luminance values and the sharpness data are read from the picture, and it's sent to our control, and the lighting adjusts based on what data it receives from that initial picture, and that is a continuous loop. It continuously cycles, and the higher definition camera, when it takes a picture, it's actually multiple pictures, it's 3. And so it brackets 3 images and then merges them into a final higher quality image at the end. And the camera only takes pictures unless we pass the threshold for 10 consecutive frames in each zone, and at least 30 seconds since the last capture. And so how do we confirm, what brightness or sharpness values were necessary to constitute a good image? Is that we conducted a noise sensitivity study for the sharpness values, and what that means is basically the measure of the sharpness of the image. And so we had 50 for night and a higher threshold for day, 150. And so on the graph, what this is showing is the blue line is the noise level for the camera that we have, and then we did a study on 2 higher noise levels just to see what would happen like in a high noise environment. And what we found is that at 50 for nighttime and at 150 for daytime, that it was robust and we were able to have a good image quality. And so it's a little misleading. As you can see in the blue line, it's above 50. Well, it's below 50 at 0, but for the red and the green, it's above 50 at 0. And so, although there's no light, it's saying that we have a high quality image, and that could be a problem. And what it's saying is there's a lot of noise. And so, to mitigate that, we added another threshold that we had to meet, which was it had to reach, like our lighting system or the lighting output, it has to be read that it's above 40 lux.
Alright, so as shown here, these are some of the images that we got with our results just with testing. So as shown, the system's HDR pipeline dramatically improves the image clarity. As you can see in that first image compared to the second image, the shadows lift as well as its highlighted area, which makes the full scene completely visible. And same with going with this, so in this before picture, this was our baseline. So when we activated our system, this is the first image it took. And as you can see, it's highlighted the sunlight, obviously, but you can still tell that it's pretty dark in some areas. So after running our system through, we basically told it that by applying the 4-break HDR stack, a Reinhardt, a clay clip, and it's able to recover both zones simultaneously. And you could really tell the details in like the objects on the side as well as the background. So for our nighttime, these are the results we got. Obviously, at night it's completely dark. So these are results when we had our system on. It was able to highlight the dense terrain as well as the walk path in the left image, and in the right image, we just went to a basic field to see how far the light will be able to cover, and it went around 20-ish meters. Was the farthest before we got completely black.
To summarize all the test results, we had about 6 criteria that we tried to meet. We did pretty well. We met 5 out of 6. The 6th one we partially met, but we had an adaptive lighting control. We met our illumination goal of at 5 to 8 meter, from a 5 to 8 meter range. We were very efficient with power. We had a max draw of 83.7 watts, which means that we can use a portable power source. We were able to improve the quality of the image, with sharpness improving up to 35 times in darkness, 10 times at night outdoors, 8.7 times in the daytime, and a general contrast improvement of 3.1 times. It's safe thermally. We ran it at full power for an hour in the sunlight, and the electrical box peaked at 105 degrees Fahrenheit. And the last one, the motion stability, it does work while we're moving it, but we realize that the faster we move it, like once we start getting around 3 miles per hour and up, the performance starts decreasing. And one way we can mitigate that is, implementing a dampener for vibration, something to dampen the vibrations, something like that. And what we achieved is that we were able to demonstrate that a closed-loop adaptive lighting and camera system is able to mitigate the high contrast lighting environment on the lunar surface. Every decision that we made, it was from analysis, simulation, and testing. We were able to test in darkness, indoors, outdoors, and in bright sunlight. And our full system runs on Raspberry Pi 5, which is very easy to integrate into other systems. These are our references, and thank you. Any questions?
All right, time for a couple quick questions.
I have a question. How long is your system supposed to run?
So with our power bank that we have, it reaches just under 1 hour, but since it's going to be attached to the lunar rover, it should be within the 4 to 5 years before we need to completely change all of our materials out. Yes?
Could you go up a couple of slides to the garage?
No?
Yeah, that's the one. And so, I didn't notice it at first. I was just looking straight out, and I see that the difference is actually over to the sides and the shadows. Is that correct?
Yes, sir. But it's also in the houses as well.
You're right. I didn't see that before. Okay. The other thing, though, and I think this is about your top 1/3, I don't see any clouds. Is that correct?
Like from this?
Yeah. Okay. All right. And so my real question then is, I think goes go back to the slide where it's the open field. And so, yeah, I think that is the one that we need to do the most testing on. Is that correct? Because right now, as we go out across the moon, we're not going to be seeing trees. We're going to be seeing little rocks and hillsides. Is that correct?
Yes, sir.
All right. Excellent. Thank you very much. Good job.
Thanks.
All right, thank you, team. Okay, our next team is Texas State, Team Boss.
Good afternoon, everyone. We are from Texas State University. We are Bobcats in Outer Space Structures, or for short, Team Boss. Our project was the Lunar and Surface Habitat Model Manufacturing. My name is Chloe. I have my team members here, Liam, John, Scott, and Tony. So really quickly, a little bit about us. We're all undergraduate mechanical engineering majors graduating this semester. This is actually our second semester working on this project. So a couple of things we would like to talk with you today, going over our project overview as well as getting into our design, verification, and then also next steps and conclusion. So NASA has a need for surface habitat modules that can support crew members for long-duration missions to the Moon and Mars. Of course, part of having a successful HAB module is making sure that we're keeping those crew members safe and alive. So some of the key functions we want to make sure that we're going to hit are, of course, providing a pressurized environment for them, something that is structurally and thermally stable. It should be able to provide efficient radiation protection for them. We want to make sure we're able to facilitate power to our major subsystems, and then also standard interfacing.
So next, I want to talk about quickly the inspirations for our design that we came up with and sort of our rationale for picking that design. So traditionally, NASA has used primarily rigid habitat modules in the past, going all the way back to the original moon missions with Apollo and more recently with Artemis. And these have been primarily orbital habitats, but there are still rigid pressure vessels that are deployed and launched in the same configuration. But more recently, we've seen things like the Bigelow Expandable Activity Module and other concepts like the TransHab that are realizing some gains in terms of launch volume being smaller, so being able to send a smaller payload up into space and get a larger interior volume. The problem with these things is that there are some issues with long-term durability and reliability with these types of modules that we would like to provide for. So our goal was to try to marry the positive benefits of both of these types of designs with our module. So we came up with the Bobcat's extraterrestrial deployable habitat, or the BAD for short. And this takes a hybrid approach. So it's an interior pressure vessel that's deployable. It ships in a compacted configuration and then expands later. And we augment that with orbital debris shielding panels that are installed on the outside of the structure. And these are modular and can be individually replaced. And we also tried to optimize for toolless, easy assembly so that the assembly process can be completed quickly. So just to recap, essentially, we want to have a collapsed configuration that we ship the module in before landing it on the surface of the moon or Mars, and then expanding it into the expanded configuration. And that lets us put more mission equipment and that supplies in the payload variant when we launch the rocket.
So here we have both of our panel styles. Both are using a Whipple shield design. So the outer casing is made of aluminum with layers of Kevlar and Nextel inside. On the left, we have the roof or the domed panel. And on the right, we have the side vertical panels, as you can see here. And we have little illustrations on how these panels would be fastened to our structure. Both utilize similar fastening techniques. So in the domed panel in the top, there is a peg that goes into a hinge, and the bottom of the vertical panel has a peg with a hinge as well. It has about 30 degrees of travel for easier installation for the astronauts. And then on the bottom of the domed panel and the top of the vertical panel, we have ball and socket friction fasteners. And then to supplement those ball and socket fasteners, we have extra protection against failure. So on the domed panel, we have another peg with a locking pin hole. And then in the vertical panels, we have two handles that would rotate about 90 degrees and push a pushing pin or locking pin into the structure, the ring structure at the top. And here is a little demonstration of the panels being installed. For the assembly of our module, it would first be decompressed with no air inside, so we would install the domed panels. We would then inflate the inflatable inside, and then put our side panels on afterwards.
Hello. So pictured here is the base of our module. This is where our panels, this is where our inflatable, this is where everything sits upon. It is 8.2 meters in diameter and is made of aluminum 2090 alloy. This gives us a total floor space of 53 meters squared. Shown here is a cross-section of our module. It is a ½ meter in depth and includes a subfloor space that we're going to show off later. Here we have our subfloor space. This allows us to store mission-critical equipment below deck, such as our gas tanks to inflate the module, as well as other things such as our pressure tanks and ECLIS. This allows for easy access to be able to work on them in a pressurized environment and keeps them out of the main floor space. By placing them under it, we can leave the interior floor space completely open, and it is flexible to be used for whatever furniture or equipment the mission requires. So, here's Jeff. Jeff is protected by our interior inflatable as well as our panels. The interior inflatable stack has multiple different layers. Each of them have an important part. For them, our first layer is a Nomex layer. This Nomex layer is fire and cut resistance. On top of that is our HDP and rubber bladder. HDP gives us radiation resistance, and and the rubber bladder is our pressure holding layer. On top of that is our MLI, our thermal insulation layer, as well as our Kevlar and Nextel. Kevlar and Nextel gives us rigidity and puncture resistance. I will turn it back off to Chloe.
So one of the really cool benefits of our design is the modularity of the hab modules. We've designed it so that each module will have 3 standardized connections, which allows for a lot of versatility. This is just a mock-up diagram of what a potential colony could look like on the surface of the moon or Mars. Of course, you don't have to attach 3 other modules to a module. You can kind of mix and match if you want to put an airlock, docking ports for extraterrestrial vehicles, things like that. One of the biggest challenges we had with the project was figuring out how we were actually going to package and launch the module. We decided to go with the SLS Block 2 cargo configuration with the 10-meter payload fairing to support our 8.2 meter diameter base. We want to make sure we're keeping our center of gravity towards the lower end of the payload, so heavy things are going to go on the bottom, such as our hardware, robotics, gas canisters. And then on top of that, we'll have our deflated core surrounded by the rigid exterior panels.
So for our design verification, we have our 8.5 meter diameter base, and that's hollow, and we wanted to make sure it wouldn't buckle. It's 3.5 centimeter thick aluminum, so to test for yielding and buckling, we did an abacus analysis, and these are our boundary conditions. We tested for the moon and Mars, and the moon was the Martian environment. So on the moon, we had a maximum displacement of 0.76 millimeters and a maximum stress of 18 megapascals. And the yield strength of 2090 is 500 megapascals, so it will not yield because we have a safety factor of around 28.
So to wrap up, I want to talk about the next steps and the future work for our module. So what we'd like to do going forward is to continue to refine our analysis, our structural analysis, including thermal analysis of the module itself and of the panels. We'd like to continue fabricating additional prototypes and improving upon the ones that we have. So, for example, the vertical panel, we made this kind of an ergonomic test bed to try the human factors, but we'd like to include the actual layers to use as a better demo. We would like to look into the power generation, interior wiring, and then do some cost of manufacturing studies and materials testing on the actual materials to be used in that hookup. In conclusion, we've created a module that could be used for long-term missions in space that satisfies the constraints for protecting the astronauts and accomplishing the mission of giving us a modular and expandable base that could be used for future missions. Thank you, and we'll turn it over for questions.
Questions?
Okay, I ask this recognizing that you are in early concept phase. Talk to me about how you're going to deploy from your launch configuration, about the astronauts in the spacesuits, and how they're going to do your steps to deploy the top surface.
So we actually have a diagram of the assembly sequence that we are thinking of going forward with. So once the lander touches down, we're assuming that there would be some sort of robotic or crane assembly to assist with getting the module actually out of the payload fairing. The site that they would want to put it on should be prepped already, so they would just place it wherever they need to put it. And then we'd unload our payload, and then we'd have our deflated bladder. We're assuming that we would have a crew of 3 or 4 crew members to assemble the module together. So once everything is laid out, they would first put on the roof panels. Each panel is around like 30 pounds on Mars, so one person should be able to pick one up and assemble it, no problem. So they assemble the roof panels on top, and then the bladder will be inflated, and then they'll proceed to attach the side panels around it. After that, they can start integrating their subsystems. So you mentioned airlocks. We would use just a standardized airlock. We were looking into dual airlocks like the Quest airlock, so having something with a suit lock and then also an airlock to kind of help mitigate dust.
Other questions? Any on this side of the room? We'll make our way over there.
Sorry, I got it first. In the slide that you showed with the small, essentially, am I understanding that correct, like crawl space underneath, where all of the, yeah. Maybe I missed it, but do you intend that once the habitats and all the walls are set up and the roof is all fully assembled and everything, that while it's pressurized, astronauts, if necessary, can access that from the inside?
Yes, the idea would be to have some access panels so that they could get in and do maintenance on whatever they needed to do. But it would be primarily closed off, but there would be ways for them to access, but it is part of the same pressurized volume.
I had a question. So if you could go back to the slide with your shielding diagram. So the one with all the layers.
Oh, I think that's here, right?
So I thought that one was really interesting because I noticed you guys were incorporating a lot of polymer materials. So I know this might be a little bit kind of later on you can think about this, but there's been a lot of research into developing sustainable polymer systems. So stuff like organic waste that you convert that into polymers. So have you guys explored any kind of renewable sourcing opportunities to build stuff? Or do you think that could be possible in your case?
So for renewable sources, I can't say that we have done renewable sources on Earth, but for sources that could be used in situ, so in situ resources, there are two main methods, either SLS, so selective laser sintering, or creation of lunar-based concrete, more than likely with sulfur. We did consider this during the earlier phases, however, it was phased out of our scope pretty early on. Thank you for the question.
I was curious how long it would take to inflate a structure of that size. Is that a quick process?
So the inflation of this is not an entirely very fast process. This is mainly because we want to do it safely. We would inflate this more than likely over the course of 2 or 3 days. During this, we would make sure that nothing is occurring, that it is in fact inflating correctly. Afterwards, we would do about a day to ensure testing of the pressure seals to ensure that there is nothing wrong with it before allowing the astronauts to take off their suits within the pressurized vessel.
All right, thank you, team. Okay, our final team this session is from the University of Houston Clear Lake, and they are the Interstellar Innovators.
Good afternoon, everybody. We are Team Interstellar Innovators from University of Houston Clear Lake. My name is Cal Harper. I'm joined with Julian Hebert, Garrett Stevens, Magali Chavarria, and Vivian Liu. And we're here to discuss our passive capture tool dock design and the side release buckle. For our presentation outline, Garrett will introduce us with our introduction, customer requirements, and relevant codes. Magali will then take over and introduce everyone to our preliminary design concepts and our product architecture. And Vivian will discuss our design specifications and safety concerns. I'll come back and do our finite element analysis and prototyping, and then Julian will close us off with our bill of materials, forward work, and conclusion. I'll pass it off to Garrett for our introduction.
Thank you, Cal. So just some background into our project. Extravehicular activities, or EVAs, are crucial for ISS maintenance, where astronauts on these EVAs oftentimes find themselves in constrained body positions. They stow their tools on something called a mini workstation swing arm, or MWS for short. And current securing methods require dedicated install actuation with switches and locks, like the on-orbit use of the bayonet and tether, and we're trying to avoid that dedicated install actuation. So our objective is to design and manufacture an EVA tool dock that allows for blind, one-handed tool installation without any dedicated actuation. So some requirements, criteria, and constraints. It needs to be single fault tolerant. It needs to be able to be blindly installed and retrievable with one hand. No dedicated install actuations. It needs to be compatible with the MWS swing arms with a 1x1 inch bolt pattern. It needs to be ergonomic and easy to use, just meaning it needs to be EVA glove friendly and non-buoyant, which would be tested at the NBDA. And we have some constraints, like we have to stay within a 5x5x5 inch volume. We cannot exceed a weight of 2 pounds on the tool dock. We can't exceed an install force of 10-pound force. And we need to be able to support at least 15 pounds of weight in Earth's gravity. So we created a house of quality to compare customer requirements with engineering characteristics to give them some measurable values, and just to make sure we hit all our marks when we were in the design phase. So some relevant codes and regulations that we followed during the design and manufacturing phase. So just to highlight too, the sharp edges and pinch points, we needed to make sure to try and get rid of these, and if we weren't able to get rid of them, like the pinch points, we needed to label them, and we also included designated touching areas and also no touching zones on our tool dock. So I'll pass it over to Magali to go over our design concepts.
Great. Thank you, Garrett. So for our last semester, we had 4 preliminary concept designs. They all focus and explore different docking mechanisms, mainly the locking mechanisms. We had the holster, the buckle, the snap dock, and the coupler. Based on our peak work, concept 2 ranked the highest, which was the buckle. So this was based on selection criteria as well as our reference point, the bayonet and tether, thus giving us the final design, the side release buckle. There was a couple changes in our concept design as well as prototyping phase. We came up with increasing the surface area of our buckle base and the pin in order to reduce stress, as well as adding a lip into the front part of our belt buckle to give it that snap fit, also giving it stability individually and also reducing stress on our spring supports. And we also redesigned the base of our buckle to replace our buckle easily in case of any breakage, saving on material, time, and money. The overall dimension for the docking mechanism itself is 3.75 inches by 3 inches by 2 inches, having a total weight of half a pound. And then a little more in depth. So the docking mechanism is consisting of 2 components. The belt component that will be attached to the MWS. This has a key feature of the taper alignment slot, giving the astronaut the opportunity to have that one-handed blind installation. And we also have the buckle and the buckle base, giving us our other locking mechanism and our curved flat springs, which is going to be our second locking mechanism. And then our other component will be the tool component that will be attached to our tool, in our case, the PGT. Some key features are the buttons and the springs to release our buckle, and most importantly, the pin that will be causing deflection on our glass springs. And I'll hand it off to Vivian to go a little more in depth on how it works.
Thank you, Magali. So here's an expanded tool component, just focusing again on the pin and then the 2 buttons and the springs. And here's a video of how it comes together. As you can see, there's the buckle housing and then the spring mechanism with the 2 side release buttons and of course the pin, and it locks into place with the bolt hole patterns. And here's the expanded view of the belt component, just again focusing on the 2 curved flat springs as well as the removable buckle in the buckle base. And here's the video of the buckle, the belt component coming together, of course focusing on the 2 curved flat springs in the spring supports and the snap fit. Here's an animation of how it works. So as you can see on the right hand side, as the buckle slides into the buckle housing, that's going to be our first locking mechanism. And then our second locking mechanism is going to be when the pin goes through the curved flat springs, it's going to cause that deflection. And then at the bottom, that's going to be our second locking mechanism. So I'm going to kind of show how it works. So we have the MWS, it's what I'm wearing right now, it's just a replica, obviously not the real thing. Our PGT, obviously not the real thing as well, and then I'm simulating this with some heavy duty gardening gloves, just to replicate the astronaut gloves. So as I'm sliding the pin into the belt component, it's gonna snap into place, and then with one hand, I can press both buttons and pull it up, and that's just essentially how that works. And then moving on, some safety concerns we do have. So in this slide, we do highlight the no-touch zones. It's not intended that the astronaut will be touching any of the belt component, but the pinch points we do have is whenever the pin slides into the taper alignment slot, that's going to be where the pinch may happen, and as well as the bottom of the buckle base, when it goes into the buckle housing, that's going to also can cause potential pinching. And then as well as the no-touch zone, like I said, it's not intended that they're going to touch the buckle, but in the case of, we do have that labeled red, and it's intended that when you're holding the tool, you're just really holding the sides and the top as well as the buttons when you're sliding it. And I'm going to go ahead and pass it to Cal for the FEA analysis.
Thank you so much, Vivian. Our FEA focuses on critical components of the side release buckle and reviews any potential failure points that we have on those structures. So our buckle base was cleared because it only experiences about 1.6 megapascals. However, our pin, we do see about 26 megapascals on the worst case scenario load. For our buckle prong, we're also seeing about a 19 megapascal load on the prong, which kind of led to a change in how we reviewed our installation forces, and then also allowed us to look at having a removable buckle to allow for rapid replacement so we can better test potential buckles. We'll go to the next slide. For our prototyping, our side release buckle, it works with NASA's operational requirements for the passive capture tool dock. We successfully are able to hold 15 pounds with the passive capture tool dock. For our fatigue testing, before the event, we've already simulated 300 cycles of undocking and docking the passive capture tool dock, and we have had no part failure yet, and that's not including all the testing that we've done during the poster evaluations that we had yesterday. Our ergonomic testing, sampling our fellow classmates, we found about an average of about 1.5 ease of use, for one being the easiest, for a blind-handed one install. And the single fault tolerance, we're able to prove that because we have a soft and a hard dock with our 2 independent locking systems, that it is single fault tolerant and will still hold the tool if any flat spring or buckle is not operational. And I'll pass it off to Julian to finish us off with the bill of materials.
Thank you, Cal. So here we have our bill of material to make one PCTD, and the total cost to manufacture one is about $28.89. That's not including the labor or the printer cost. And the main materials used is PLA, along with a small number of sheet metal screws,
and a spring assortment kit. Overall, the design is low cost, uses simple parts, and is easy to manufacture. Next, I will talk about the forward plan and suggestions for improvement. Moving forward, we plan to do more testing, including possible testing at the MBL or student testing by submerging it underwater to better match real conditions. We also want to test the design print using tough PLA to study how the material behaves, since PLA can absorb water and expand. For future design and real space applications, we may look into stronger materials like space-grade aluminum and make changes to the curved flat spring geometry to better match the new material. For improvements, we suggest adding threads to the spring supports to make assembly easier and help prevent cracking. And finally, to conclude, our design meets all the required constraints and goals. It allows blind, one-handed installation and does not require active actuation. It is also single fault tolerant, supports up to 15 pounds and stays well under the weight limit at about a ½ pound. Overall, the side of this buckle design improves safety and tool handling for astronauts. And here are some of our references we used. And I'd like to just thank our professor, Dr. Villa, and TSGC for this opportunity. And are there any questions? Thank you.
Questions for the team?
Okay. So when you're attaching, you've got to be able to reach around at both sides of it. Have you done this with different size hands to be able for matching up with other size people?
Yes, sir. So, great question. We did do the ergonomic testing or ease of use, like Cal mentioned earlier, where we did test it within our senior design class. They vary in different hands and both female and male students. And on that scale of about 25 students, we did have that rating of 1.5 out of 10, with 1 being the easiest and 10 being the hardest. We also did test it with different gloves. So this one's a heavy-duty gardening glove, and we also tested it with like a traditional oven mitt, which doesn't have any hand or like fingers.
You might also try like a hockey glove. It's a little bit stiffer, and it's not quite the same, but it's got some similarities.
Yes, sir. Thank you. Thank you for the suggestion.
Other questions? Way in the back.
Firstly, amazing design. One thing I'd like to ask, since this is going to be out in space, it's very possible that it will interact with the sun. So, at those higher temperatures, have you guys accounted for thermal expansion and possible binding of that groove with the tool that you're inserting?
So for this challenge specifically for our design, so when we went to the Micro G Next session, they did, that question did come up to do thermal analysis on our tool dock, and Micro G Next did say that we shouldn't worry about that, or that shouldn't be a part of our design for now. We're more focused on the structural and mechanical aspect, and then once selected, while we move forward in testing, that we'll consider that. And that's why we said for the forward work, we might consider a different material, such as the space-grade aluminum.
Thank you.
All right, thank you, team. All right, and that concludes our afternoon presentation. So a big round of applause for all the students. You have about an hour to go get some snacks, go back to your posters. We'll finish up the judging and scoring and be back for recognitions and awards at 4:30, starting with a group picture, which will be right outside. Thank you. All right, welcome everyone. Welcome back. Yes, round of applause for everyone, please. So this is the recognition and awards for this evening. We have a lot of people to thank. Thank our guest speaker yesterday, Heidi Paris. Special shout out to all of our showcase judges. Give them a round of applause. Students, please thank again your NASA mentors and your faculty advisors and other supporters. And a big thanks to all the enthusiasm and brilliant ideas that the students and teams have come up with. Thank you so much. All right, so the judges' scores have been tabulated. We have best video, best poster, best peer review, best oral presentation, and those scores are combined into the top overall design challenge team. Student gets scholarships. Fourth place gets $500 per student. Third place $600, second place $750, and first place $1,000 scholarship per student. Are you ready? Yes. All right. Best video. In fourth place, UCL Interstellar Innovators. In third place, Texas State Password Bobcats. Second place, best video, Texas State Rad Dog. And the best video this semester, Space Depot. And a reminder, you can find all the videos on our YouTube page. All right, now the best poster. Our judges worked hard on these, and yet we still have some ties. So in fourth place, 12th Man in Texas State Boss. Third place, Space Depot. In second place, Cosmic Command and Interstellar Innovator. And the top poster this semester, Team Daedalus. Today's events. Oh, this was yesterday, sorry. Peer review. All of you scored each other, and this is what the teams came up with. Fourth place, Texas State, Password Bobcats. In third place, 12th Man. Second best peer review, Mercurian. And top peer review this semester, Aggie Nuts. Okay, now on to today's oral presentations. Aren't you all glad that's over? All right, you all did fantastic. Fourth place, Texas State Password. In third place, Rad Dog. In second place, Mercurian. And the top oral presentation this semester, Aggie Nuts. Okay, those are the scores that went into the final calculation. So let's have a drum roll now. Fourth place, top design team, Interstellar Innovators. Drum roll again. Casper Bobcat. Another drum roll. Second place. Aggie Knots. And our overall top design challenge team this semester, drum roll. Mercurian. So every semester, the teams get better, the scoring gets more competitive, scores get higher, they get closer. We're seeing more ties. Everyone did fantastic. So again, give everybody a round of applause. All right, final reminders. Your final reports are due May 8th, please, with your outreach report, if you did that. Team funding, if you haven't gotten it already, check with your institution on that, and check with Talia. We'll coordinate to make sure you get funding. Top 4 teams are going to get scholarships. Look for email from Talia on how to get those awards. And then, of course, watch your email. We'll send out the team scoring, all the photos that have been taken today, and special team certificates for all of these top places. We're going to send you a showcase feedback form just to keep us improving the event every semester. Our independent evaluator, if you didn't meet her, Arthi Singh, she is our evaluator for the project and helps us improve as well. Look for a form from her. And then in August, we'll have the fall program announcement. So congratulations if you're graduating. If you can, pass your project on to the next generation. We hope to see many of you in the fall. And that's it. Drive home safely. Thank you.